All right, today we will begin with a new chapter of our lecture, namely quantum electrodynamics, one of the most successful theories in physics, the theory with the most precise predictions which are also tested and compared to experimental data and which are confirmed by experiment. Therefore, it is a milestone in theoretical physics and of course the basis of the standard model. Actually, QED is a part of the standard model of particle physics. It describes electromagnetic interactions with charged particles and the photon. And it is correct. It is correct as a low energy limit of the standard model in a well-defined way. Therefore, QED can be studied in isolation, and the study of it is not wrong. It will be superseded by the standard model, of course, which brings in extra features, but in a certain approximation, the QED predictions remain correct. So what I want to do in this section here is, first of all, we will define QED, and I will give you two different motivations for the QED Lagrangian, which have to do with gauge invariance. Of course, you know the QED Lagrangian, I suppose, from other lectures, but we will do both motivations here in order to give you as many connections to other theories as possible. And one of them is the one that you already know from our free field discussion, and the other one will be new. We of course want to discuss some calculational techniques which are simply useful and necessary in order to deal with QED calculations. And then we will discuss some physics, which is really QED physics and quantum field theoretical physics discussions having to do with spin, angular momentum, and also energy, high energy, low energy limits. These sort of things will be discussed, and so you see how the interplay between those physical quantities is in the context of spin 1/2 and spin 1 particles and their interactions. And finally, we will come back to gauge invariance, and I'll tell you what we will call here the magic of gauge invariance, because it implies very, very mysterious and deep but very important relationships we'll discuss. So let us begin. With the definition of QED and the discussion of gauge invariance. And we first begin with the first motivation, which comes from our discussion of free fields. Let's call it free field consistency. So, here in this approach, we have the following starting point. We start by saying we know something, namely we have observed somewhere that there exist electrons and positrons and photons. And we want to formulate a theory which correctly describes electrons, photons, and positrons. E plus, E minus, and gamma particles. And we want to describe them and their interactions. So, what we know from our chapter 2 of the lecture is how to describe the particles without interactions in terms of a free quantum field theory. So we know how to describe them in terms of free fields. And the description leads to a certain Lagrangian, which I call L0, which is a free Lagrangian describing the free electron, positron, and photon. That is what we know. And then there is an outcome, namely our study has given us some results. Not only do we know the precise form of the Lagrangian, but we know in particular that there is a difficulty in connection with the spin 1 massless particle because of that mismatch of degrees of freedom, right? We had this mismatch 4 versus 2 degrees of freedom. And the impact of that mismatch was that in the quantization of the photon, there are difficulties, and the difficulties can be solved in different ways. And we have in particular discussed 2 different solutions, namely on the one hand the Gupta-Bloiler formalism, and on the other hand Coulomb gauge quantization. In the Gupta-Bloiler formalism, let us not write down everything, but in the Gupta-Bloiler formalism, we treated the photon field in a Lorentz covariant way. We introduced the so-called gauge fixing term into the Lagrangian, which breaks gauge invariance. As a result of this, we can quantize, and we get 4 degrees of freedom in the quantum theory from the photon field. But the Hilbert space is not positive definite, it has negative norm states, and it is difficult to interpret. And in order to get a consistent interpretation, we need to go to equivalence classes and physical subspaces. And one then has to make sure that interactions are compatible with the definition of those equivalence classes and the physical subspace. So in principle, Lorentz transformations are the main thing that we should worry about, and Lorentz transformations mix, first of all, physical and unphysical states. But by going to the equivalence classes, we can define Lorentz transformations consistently only on the equivalence classes, which is a positive definite norm Hilbert space, and therefore the equivalence class structure must be compatible with interactions. Otherwise, Lorentz invariance and the interpretation of the theory is broken. In Coulomb gauge, the photon field operator A mu is directly not Lorentz covariant. It does not transform with lambda mu nu, but in a more complicated way. And then we have to ask ourselves whether interactions are Lorentz invariant if something interacts with a non-Lorentz invariant or covariant A mu field operator. Okay, so in both approaches we have some problem. And we already did the analysis in great detail, and let us just write down the result, namely Lorentz invariance and this consistency with equivalence class structure implies the following, namely that interactions should have the following form. An interaction Lagrangian is given by minus A mu times J mu some current with a conserved current. J mu. That is the main point, that we need interactions with a conserved current, and if we have such a conserved current interaction where d mu j mu is 0, then we get consistency and our theory can be interpreted. Therefore, since we know all that, we can now answer the question, what is the simplest theory for electrons, positrons, photons with an interaction which is consistent with this analysis? And the simplest theory would be one where we have an interaction of that kind, where A mu interacts with a conserved current, and the conserved current should be consisting of electron and positron fields. And so we can write down the simplest such Lagrangian, and that will be the QED Lagrangian. That is then our ansatz. So the simplest L int of psi, psi bar and A mu of this kind. And this gives us L QED is equal to L0 plus L int, which is equal to the following: psi bar I d slash minus m psi minus 1 over 4 f mu nu f mu nu. This is the free Lagrangian, and then an interaction Lagrangian minus e q psi bar gamma mu psi times a mu. And here in the second line we have it. We have an interaction between a mu and something that looks like a current, and that object here, this current, is indeed conserved, as I will show in a moment, and therefore this is a Lagrangian of this kind, and it is the simplest because the interaction Lagrangian consists of a single term, which is the simplest that you can build out of the fields, and that has this property. So this is our first motivation for QED. It is the simplest theory with an interaction which is consistent with the free fields electron, positron, and photon. So, and now we can discuss the properties of this Lagrangian, and I'm sure that you have seen in other lectures the discussion that will now follow, but nevertheless let us do it. Namely, let us prove that this is gauge invariant and that the current is conserved. But this is a calculation that you are certainly familiar with. So the claim is that this Lagrangian is gauge invariant. And I will tell you exactly what I mean by this. And even more importantly, at this point, the current is conserved. And the current conservation, of course, follows from Noether's theorem from the symmetry connected with gauge invariance. Actually, I will be a little bit precise and maybe more detailed than you expect me to be, because I will distinguish here between global and local transformations. First, let's consider global symmetry. Or first transformations, global transformations. R psi of x goes to e to the minus I e q alpha times psi of x, and alpha is a constant. Okay? So this e q in the exponent is pure convention. Please do not give too much meaning to it. It's a useful convention, but it's a number prefactor, and the main point here is that we do a phase rotation with an exponential phase with a parameter alpha, which is a constant. So, and this is the transformation. The electron field transforms in this way by a complex phase, and the photon field does not transform. It is invariant under this global transformation. A mu of x remains what it is. Then there is also a local transformation. Where the phase becomes x dependent, and let me write it down separately. Psi of x goes to e to the minus I e q alpha of x times psi of x. And alpha of x is now a function of.
طيب هنا لدينا وقفة قليلا. طيب الوقفة في أنه عند دراسة الانتراكشن نحن نعلم من المحاضرات السابقة أننا استطعنا أن نجعل لاجرانج انتراكشن جيج لوريس انفاريانس، اللي هو بعد ما عملنا جيج فيكسينج وطبقنا في المعادلات وجاءتنا الفايمر رولز. هذه تعتبر لورنس انفاريانس، وتعتبر هذه المعادلة بما أنها لورنس انفاريانس النتائج التي سنتحصل عليها وكأنها يعني تدخل في سياق اللورنس انفاريانس. هذا لا يصف لنا الانتراكشن. الانتراكشن كما ذكرت في محاضرات عديدة أننا نفرض على الأمر ليس لورنس انفاريانس، بالعكس، ونحاول نجعله لورنس انفاريانس. يعني لاجرانج اوف انتراكشن اللي هو انت محاضرات السابقة جعلناها لوريس انفاريانس، هذه المرة سنجعلها غير هي نط لوريس انفاريانس. سنعود كأنها ليست لوريس انفاريانس، لكن سنجبرها أن تكون لوريس انفاريانس. سيحصل هناك عديد من الكونتراكشنز، هناك حدود لا يمكن أن لا تحصل لها كونتراكشنز. هذه الحدود تعتبر هي الحل لمعادلتنا هذا أو للقضية التي نحن في صددها، مثلا الكيو دي انتراكشن مثلا بين الإلكترون والفوتون، الإلكترون والإلكترون وهكذا. ويشترط في كيو دي طبعا أن يكون الفوتون داخلا في هذه المعادلة، لأنه الجيج فيكسيرا ولا الجيج انفاريانس. الآن نحن نعوض على الإلكترون على الفوتون، لأن الفوتون الوحيد الذي يتحمل يسمى بالجيج ترانسفورميشن، الجيج انفاريانس في معادلته. الإلكترون ليس لديه هذه الخاصية لأنه هو يعتبر كونسترينس كلاس 2، فالكلاس 2 لا يعتبر الجيج انفاريانس أو الجيج ترانسفورميشن، أو لا يحتمل، ليس لديه في هذه الخاصية، برغم أنني لا أتفق، لكن تعال نقول أنه ليس لديه هذه الخاصية. وبالتالي ما لديه هو الفوتون أو البوزون 1، البوزون سبين 1. بالتالي نستطيع أن نطبق هذه الإجراءات على الجيج ترانسفورميشن بحيث أن نجعله انفاريانس، بعد ذلك نجبره أن يكون انفاريان، والنتائج التي سنحصل عليها هي نتائج التفاعلات. هذا واضح من خلال الشرح السابق الذي شرحته في نظريتي، بحيث أنه فعلا هو داخل التفاعل هو السيمتري ينكسر، فبالتالي ممكن نعمم هذه النظرية على جميع السيمتريز، يعني ليس في الجيج، يمكن نعممها على جميع السيمتريز. نجعل الماتر انتراكشنز نجعلها نوت لوريس انفاريانس ونحيلها على انها لوريس انفاريانس. وهذا واضح اذا جعلناها يعني داخل التفاعلات، جعلنا انه التفاعل يعتمد على اكس اللي هو على المسافة، وربما الكتاب الاخير يذكر هذا. نجعل المسافة ان التفاعل يعتمد على المسافة، ثم بعد ذلك يعني نعوض ونشتق بالنسبة لإكس، وبعد ذلك بعد أن جعلناه يعتمد على المسافات نجعله يعتمد على الفضاء، نجعله بعد انفاريانس، بعد ستخرج نتائج في شكل ماتريكس، هذه تكون نتائج التفاعلات. هكذا تحل الأمور، وهكذا هو الآن سيحل الكيو دي بهذه الآلية، والنتائج التي نتحصل عليها هي نتائج التفاعلات. يعني فكرتي أنا عن أنه التفاعل السيمتريس مكسورة الآن يتم تطبيقها في الكيو اي دي، يعتبر أنها سيمتريس مكسورة، ثم بعد ذلك يصيغوا معادلاتهم ويرجع مرة أخرى أن يقول السيمتري غير مكسورة. النتائج التي ستحصلون عليها هي الفرق الذي تحصلون عليه هو الفرق الناتج من كسر هذه السيمتريس. طيب تعال نواصل.
Of X and the photon field transforms in a non-trivial way into itself plus d mu of alpha of x. And just to highlight the difference, all the transformations except for the last one are what we call homogeneous. Namely, on the right hand side you get something proportional to the left hand side. But this one is inhomogeneous. There is a term which is not proportional to the left hand side. Therefore, let me highlight this. This is an inhomogeneous transformation. And And it's the feature of the gauge fields, as we call them, that they have these inhomogeneous gauge transformations. So, and now we make the statement that the QED Lagrangian is invariant under both. And first of all, let us look at the global transformation where we have a constant phase. If you look at the Lagrangian, then it is trivial to see that the phase drops out and therefore the Lagrangian is invariant, because I didn't write it down, but psi bar transforms of course with a complex conjugated phase, and therefore since the phase is constant, the derivative doesn't do anything to it, and therefore between psi bar psi the phases just drop out, and they drop out here in the derivative term, in the mass term, and also in the interaction term. The photon field is constant, therefore the Lagrangian is obviously invariant under the global phase transformation. So I will not even bother to write down anything. For the local transformation, it is of course much more complicated to see. The question is, do you want me to write down some details, or is it known sufficiently well to you? Because it's done in other lectures as well, right? So therefore we can just say that this is a true statement, and proof, see other lectures. Good, but we will shed light on the invariance in many different ways in the following minutes and hours. So, but let me state one thing about global and local. The global transformations, they look like a subset of the local ones, right? And so often one doesn't distinguish between global and local. You just write down the local ones, and you can then set alpha to a constant and get that clearly. But you can actually mathematically distinguish between the two if you say that in the local case the alpha of x should satisfy a boundary condition where it goes to 0 at infinity. Then a constant phase rotation is not part of the local transformations. And so let me write that down. Global is not a subset of local if you impose alpha of x goes to 0 for x going to infinity as a boundary condition. Then you can mathematically precisely define the space of functions which are allowed here in the phase rotation, and a constant function is not allowed, and therefore you have two different symmetries of your theory which you can distinguish, and you can in principle always distinguish which consequence follows from that and which consequence follows from this. But of course it's often fine to just unify it and simply say you have arbitrary functions alpha of x with no boundary condition. So most of the time this is good enough. But it's nice to know that you can in principle distinguish. Okay, so we do not need to prove it. But what we should definitely prove is the current conservation. And this follows, of course, from Noether's theorem. Namely, we apply Noether's theorem. And now a question to you, since we have now the possibility to distinguish local and global, which symmetry should we use in order to apply Noether's theorem and derive the conservation of the current J mu? What is your guess? The global transformation is enough. So that's exactly right. We need only the global transformation. and then let us do the derivation. So I told you that Noether's theorem is always derived by taking the Lagrangian and applying the symmetry transformation in two different ways. One way is the...
طيب لماذا في النيزر كرنت نطبق فقط الجلوبال؟ أولا نيزر كرنت هي تطبق السيمتري، لكن كما ذكرت أن النيزر هو أصلا السيمتري عندها مكسورة، وإلا لما خرج هذا الكرنت. هذا الكرنت خرج من أجل استعادة السيمتري. إذا طبقت الجلوبال ترانسفورميشن وأصلا لك السيمتري مكسور، فهذا يعطينا مباشرة أن هذا الجلوبال اللي هو الفيز اللي أدخلناه الإي أو سي ناقص أي سيتا ألفا سيخرج لنا مباشرة في تيار نيزر، لأننا أدخلنا حد في المعادلة. هذا الحد لم نتأكد منه أن يكون لوريس انفاريانس إلا في حالة يكون مضروب في نفسه، يعني مضروب في الكومبلكس كونجيجيت له. إذا كان مضروب في الكومبلكس كونجيجيت فهو بالطبع سيكون لوريس انفاريانس، لكن في تيار نيزر هنا ربما لا نتحصل أن نضربه في الكونجيجيت في الكومبلكس كونجيجيت. لماذا؟ لأنه الأمر بسيط، أنه هو أولا في الانتراكشن هنا الصاي بار والصاي هذه يعطينا كومبلكس كونجيجيت مضروب في بعض، بالتالي الفيز أو الإي أو سي ناقص أي سيتا ألفا أو أي كيو ألفا سينتهي، لكن الإي سيكون هناك اختلاف. ونيزر طبعا تعتمد على المشتقة كما سيذكر الآن، أننا نجري المشتقة في اللاجرانج ونجري التغيرات في اللاجرانج. أول شيء هنعمل تغيرات في الفاي والإيه. الفاي وإيه سنعمل فيها تغيرات اللي هي بإضافة الدلتا، ونحسب الدلتا اللي هو دلتا فاي ودلتا إيه، ونعملها argument on one أو constant أو the same، نجعلها argument in the same x same argument، أو يعني بعد ذلك نعوض نحسبها بواسطة التايلور اكسبانشن اللي هو البلو برنت التي ذكرها الصاي بالنسبة للصاي والإيه، الصاي والفاي والإيه واللاجرانج. بعد ذلك نعوض مباشرة في معادلة نيزر اللي هي مشتقة اللاجرانج بالنسبة لمشتقة الصاي. هذه كلها تأخذ مشتقة ومفترض تساوي اكس. الاكس هي عندما تعوض على اكس رو، لما تعوض اللاجرانج بالصاي بالاكس بالدلتا وتجعلها يعني تدخل مفكوك تايلور، الحد الذي يأتينا يعتبر اكس. بعدين تطبق في القاعدة العامة بتاعت نيزر اللي هو مشتقة الصاي بالنسبة لمشتقة الاكس، تفاضل ال الأجرام كله بالنسبة لتفاضل اكس، وهذا هو كلها داخل مشتقة ناقص اكس رو. ليست مشتقة الأجرام بالنسبة لمشتقة صاي أو ايه، بعد ذلك ناقص اكس رو، والنتيجة التي ستتحصل عليها هذه نساويها بالزيرو، لأنه المشتقة ستكون مشتقة كلية، لأن هذه كلها تساوي جي، وجي مشتقة له يساوي زيرو. جي مشتقة له يساوي زيرو، إذا قلنا جي مشتقة له يساوي زيرو هذا نوع من السيمتري الذي رجعنا هذا السيمتري، وهذا السيمتري يكون في ما لا نهاية. إذن مشتقة إذن تيار نيزر عبارة عن تيار محلي، وهذا التيار الاشتقاق له يساوي زيرو في ما لا نهاية. إذا رجعنا للتناظر مرة أخرى في نيزر والتناظر مكسور، لكن رجعناه مرة أخرى في نيزر. الذي يأتينا هذا هي كتل تحاول استعادة التناظر في نظرية ثانية. في نظرية نيزر مفترض هذه الكتل كلها نسويها بالزيرو، وبالتالي هذا التيار كله الذي يخرج لنا المعادلة التي تخرج لنا نسويها بالزيرو، وبالتالي يكون لدينا معادلة نيزر. بعد ذلك نجعل هذه الكميات نعملها اوبريتورز، وأيضا بعد ما نعملها اوبريتورز نطبقها في ساي لنأتي بالسبين وما إلى ذلك.
Explicit way, namely you take the actual definition of your symmetry, plug it in and calculate the result. If we do that here, the Lagrangian is invariant, therefore the explicit calculation gives us that LQED goes into LQED, it is invariant. But then there is also a generic way, which is always possible, by simply saying that LQED becomes L of psi plus delta psi, psi bar plus delta psi bar, and so on. In particular also derivative of psi goes to derivative of delta psi, and so on. And this second generic way how to transform the Lagrangian is of course always the same as the original QED Lagrangian with the untransformed field arguments plus an infinitesimal term from the derivative of LQED with respect to delta psi times delta psi, and also derivative with respect to derivative of psi times delta of the derivative of psi. And then you can apply the equation of motion onto this transformation term, and you obtain a total derivative, namely d rho of the derivative of the Lagrangian with respect to d rho psi times delta psi. In principle, there would be many more terms for all fields of the theory. In this case, you would have a term with psi bar and also a term with a mu. However, in the concrete case, a mu is invariant, therefore there is no term with delta a mu, and psi bar, the Lagrangian with respect to doesn't depend on the derivative of psi bar, therefore psi bar also doesn't appear here. Therefore this is directly the result. And then we get this is equal to that, therefore that quantity here is zero if the equation of motion are valid, and we have our conservation law for a conserved current. So then we can evaluate the square bracket. What is the square bracket? It is the derivative of the QED Lagrangian with respect to d rho psi. D rho psi appears here, and the derivative is psi bar times I times gamma rho. So then we have, this is I times psi bar gamma rho, then times delta psi, and delta psi is the infinitesimal variation of the field, which is minus IEQ alpha times psi, times minus IEQ alpha times psi. So and that can be simplified, I times minus I times alpha, simply alpha times E times Q psi bar gamma rho psi. And so our current was already defined. The current is such that minus A mu J mu is equal to this. So the current is E times Q times psi bar gamma mu psi. So therefore this was equal to alpha times our current J rho. And then the Noether theorem directly has proven that this quantity is conserved, and that is up to the factor alpha. It is our electric current J rho. So indeed 0 is equal under the equation of motion to d rho j rho.
طبعا حسبها بالطريقة المختلفة من الذي قلتها. طبعا هي ليست مختلفة كثيرا، لأنه أنا كنت سأحسب الدلتا فاي سأحسبها بالطريقة الصعبة، لكن الطريقة السهلة هو فقط من الجيج ترانسفورميشن. هذا هو الجيج ترانسفورميشن. من هنا طوال جاب الدلتا من هذه طوال جاب الدلتا فاي. أنا كنت سأحسبها بطريقة أخرى اللي هو طريقة التايلور اكسبانشن وما إلى ذلك كما ذكرت، والA أيضا طريقة التايلور اكسبانشن، واللاجرانج طريقة التايلور اكسبانشن، ثم بعد ذلك نطبق في المعادلة. هو حسبها فقط أن الدلتا لا تحتاج إلى التايلور اكسبانشن، إنما فقط تحتاج إلى نكتبها مباشرة. هذا ما توصل إليه هو شيء جميل جدا. هذا كله في نطاق الجلوبال طبعا مفترض الألفا المشتقة تكون تساوي 0، وهذا بالنسبة للجلوبال، وفعلا هو سواء بالزيرو، والنتائج التي نتحصل عليها ستعبر عن التفاعل.
Okay, and maybe I can add once again the definition. J rho is equal to E times Q times psi bar gamma rho psi, and the interaction Lagrangian is minus A mu J mu. Then it's all collected. So that is our first motivation of QED. Starting from the particle content and the knowledge how these particles can be described in a free quantum field theory, we end up with practically a unique simplest interaction term, namely this one here in the second line. The Lagrangian has these two symmetries, global and local phase invariance or gauge invariance, and from the global invariance there follows current conservation, and the current conservation is, as we know, necessary for the consistency of the theory. Good. Any questions to this first motivation and the definition of QED? Then we will move on and go to our second motivation, which is very different. The second motivation is something that you certainly already know, because I assume that in some lectures like particle physics lecture you have at least alluded to this argument, but I think that most likely I will present it in a way which is a little bit more complicated than what you are familiar with, because I want to point out a few extra details and a few extra connections, and to describe it in a much more general way. What I'm talking about is this typical recipe where you say, I start from a Lagrangian for the electron field psi, which has a global phase invariance, and we promote the global phase invariance to a local phase invariance, and by promoting this and requiring this additional local symmetry, we must introduce a vector field in order to make the Lagrangian locally gauged. Lecture, you have at least alluded to this argument, but I think that most likely I will present it in a way which is a little bit more complicated than what you are familiar with, because I want to point out a few extra details and a few extra connections, and to describe it in a much more general way. What I'm talking about is this typical recipe where you say, I start from a Lagrangian for the electron field psi, which has a global phase invariance, and we promote the global phase invariance to a local phase invariance, and by promoting this and requiring this additional local symmetry, we must introduce a vector field in order to make the Lagrangian locally gauge invariant, and then we derive and motivate in this way the QED Lagrangian. This is the sort of idea, but I will present it in a way which is possibly new to you and points out some additional connections which are actually quite important. So this second motivation two is geometry. And actually
طبعا الجيومتري هنا في غاية الأهمية، وهذا الجيومتري هو الذي جعلني يعني مندهش حتى الآن. لما عرفت هذا الأمر جعلني مندهش حتى الآن، وهي كانت الفاتحة الخير لمعرفة أن لجرانج التفاعل أو الكيو دي تعتبر النقيض مباشرة للنسبية العامة. النقيض بحيث النسبية العامة تعبر عن كيرفيتشر مقابل طاقة مكثفة. هذا الكيرفيتشر يقيس ويزيد وينقص عن طريق الحد الثاني اللي هو ناقص جي ميو نيو في ار سكيلر. غير أن اللجرانج في انتراكشن هنا في الكيو دي لا تعتبر كيرفيتشر، تعتبر النقيض اللي هو الطاقة المطرودة من التفاعل من أجل تقليل هذا الكيرفيتشر. فبالتالي كما ذكرت أن اللجرانج يأخذ لديه نصف الحقيقة، لأنه يعتبر طاقة مطرودة من التفاعل، تيار مطرود من التفاعل. هذا التيار يعطينا فكرة عن الكيرفيتشر، لكن ليست كل الحقيقة عن الكيرفيتشر، لأن هناك آليات أخرى استعملها الفضاء ثنائي الأبعاد نحن لا نعلمها، مثلا تضخيم الفضاء تحت هذا الكيرفيتشر الليزبين. طبعا واضح أنه التيارات التي تخرج لها ليزبين أيضا. عندنا طرد الكتلة، طرد الطاقة، طرد الكتلة يظهر في تيار نيزر. هناك طرد الطاقة يكون في شكل فوتون أشعة كهرومغناطيسية وهكذا، وربما يظهر هذا في تيار نيزر أيضا لأنه موجود ال ميو موجات الجاذبية غير موجودة. إذا التشابه العميق بين الكيو دي والنسبية العامة هو ما جعلنا أنا استنتج هذه الأشياء. طبعا الآليات التي غير مذكورة في تيار نيزر وغير مذكورة في الكيو دي هي صغيرة جدا بمقابل التفاعل، لكن تصبح كبيرة إذا الطاقات العليا. لهذا ذكر البروفيسور في بداية محاضرته أن الكيو دي تفسر عند الطاقات الدنيا، لأن عند الطاقات العليا تصبح بلو أب، لأن البرتبيشن ثيوري أصلا تصبح بلو أب، يعني تصبح قيمها كبيرة جدا. الحدود العليا لن تصبح حدود صغيرة فيما بعد ذلك، إنما ستكون حدود عظمى جدا. وهذا طبعا يتفق مع نظريتي، لأنه عند الحدود الصغيرة أو عند الحدود العليا نحن سندخل، هذا يعني أننا سندخل كملاحظين سندخل إلى داخل التفاعل وسنختبر أشياء ضخمة جدا. إذا البرتبيشن ثيوري لا تنفع معها أو تصفها، لكن يجب أن نأخذ في الاعتبار أن البلو أب الذي يحصل في البرتبيشن ثيوري إنما يفسر تفسيرا صحيحا ويعبر عن ملاحظ كان موجود في الخارج ودخل إلى الداخل. يعني مثلا مثل ماذا؟ مثل ملاحظ ضخم جدا جدا ويرى حركة البشرة على الأرض، أو يرى مثلا التأثيرات التي تحصل على الأرض. بعد ذلك أصبح هذا الملاحظ يصغر إلى أن يوصل في حجم البشر. هل سيرى نفس الفيزياء؟ لا. عندما كان ضخم هناك تفاصيل لا يراها، مثل حركة البشرة على سطح الأرض، حركة العربات، حركة الطائرات، حركة هذه الأمور حركة الزراعة. الزراعة لديها حركة نحن نراها الآن، لكن هذا الملاحظ الضخم لن يرى هذه الحركة، لأن هناك تايم دايليشن ضخم جدا جدا يظهر عنده. نحن نرى بصفتنا العادية، لكن هو سيكون في يختبر تايم دايليشن، لأن الفضاء لديه أكبر من فضاءنا نحن. حركة النمل لا يراها أبدا. إذا كان حركة الإنسان لا يراها، فإن حركة النمل لا يراها. كل الحركات البطيئة يراها، كل الحركات السريعة لا يراها. بعد ذلك جاء هذا الملاحظ صغر حجمه وأصبح بقدر حجم البشر. أولا سيكتشف أن هذه الأرض ضخمة جدا جدا ليست صغيرة، بالتالي الفيزياء التي تطبقها في الأرض باستخدام البرتميج ثيوري لا يمكن تطبيقها الآن، لأن الأرض ضخمة جدا جدا. هذا هو البلو أب أو التضخم الذي يظهر في معادلة البرتبيشن، ويجب أن نأخذ به عين الحقيقة ونعمل عليها لكي من أجل أن نجد نجد هذه الاختلافات. تجد هذه الاختلافات في بين النسبية العامة والكيودي. فقط هو الملاحظ هو الذي يختبر هذه الاختلافات. الآن هذا البروفيسور سيتحدث عن الجيومتري، وسيشابه تماما بين الكيودي والنسبية العامة في صيغة جميلة جدا جدا أنا لم أراها في المحاضرات السابقة، أو لم يكن بهذا الوصف الجميل في المحاضرات السابقة. لهذا نعتبر هذا البروفيسور من كنوز التي لدي ومحاضراته، بالرغم من أنها قد تشابه كثير من السلاسل السابقة، لكن أنا أعتبرها هنا هذه السلسلة متعمقة أكثر، لأن هذا البروفيسور هو متعمق أكثر في هذا الأمر. طيب تعالوا نواصل.
So please keep in mind the thing that you know. Actually, who knows what I'm talking about? Do you all know what I'm talking about? This typical recipe of promoting global invariance to local invariance, writing down covariant derivative. Somehow it seems not totally familiar, but it's okay. I mean, anyway, we will do it now. Okay, but if you know what I'm talking about, then keep this in mind, and then you can compare to what comes now. So there is a deep relationship between what we will do now and general relativity, which I want to immediately point out. And historically, this relationship to general relativity was used very often. And so let us start in a very simple way. That's why I write in yellow. It's not yet QED, not yet general relativity, but let us simply think about geometry. Think about a plane, let's say the blackboard plane, which is a two-dimensional plane, and on this plane you can have vectors defined, or physical vectors. For example, electric field could be a vector. Here there is an electric field pointing in this direction, and at the other point there is also an electric field vector pointing into the same direction, and let's say physically those two electric fields are the same. That means now physically the two vectors are equal. However, let us now imagine you describe the plane not by Cartesian coordinates, but by some other coordinates, for example, by polar coordinates. So it's a polar coordinate system with r and phi, and you want to describe the electric fields in polar coordinates. You have here two equal vectors, physically equal, but you describe them in polar coordinates, and because they sit at different points, you know the coordinates in polar coordinates for the equal vectors are actually different. So there is something going on which is a little bit complicated. The physics is simple, two equal vectors at different points, but the description is difficult because you want to describe this in terms of a non-Cartesian coordinate system, for example, polar coordinates. What do you need to do in order to do such a description? So first of all, you have different coordinates. And the mathematical thing that you want to discuss is what is the relationship between two vectors sitting at different points which are however physically equal. And the notion that is introduced is the so-called parallel transport. That is parallel transport. So for example, you take this vector and parallel transport it to another point. And if you have not a Cartesian coordinate system, the coordinates might change, although the vector physically remains the same. So from this discussion, we get the idea of the notion of parallel transport. And if you really have a plane, a normal plane where you have polar coordinates, then of course you can go back to Cartesian coordinates. In Cartesian coordinates, you know everything. You know, of course, what it means that the vector is physically the same. Then you can calculate from Cartesian coordinates the polar coordinates here, and you get exactly what you need to know about this parallel transport. So it's clear what you can do in principle. But can you always find a Cartesian coordinate system? Here you can, but imagine you want to do geometry on a sphere. For example, on the Earth, surface of the Earth. So let's do geometry on the Earth's surface, and then you also have here a point on the surface where there is a physical vector defined, for example, an electric field vector. And you want to parallel transport this electric field vector to another point on the surface of the sphere. Then you cannot go back to a Cartesian coordinate system in order to do this parallel transport. And so parallel transport is really something deeply necessary, fundamentally necessary in order to define something like equality or difference between vectors which are defined on such a curved surface. But actually, you can solve this problem because even though there is not a global Cartesian coordinate system, you can always locally approximate the coordinate system by Cartesian coordinates, and that is good enough, because then locally you can do what you did here, namely locally for infinitesimal distances, you can always go back to a Cartesian coordinate system. Then you know what parallel transport means, and then you go back to your curved coordinates, and you know your parallel transport also here. So local Cartesian coordinates are all you need in order to have really a correct notion and understanding of parallel transport. And then for finite distances, you can integrate or derive differential equations how the coordinates need to change, and then you get whatever you need to know. Okay, so this is background information, and to give you sort of a mindset, what does that mean for QED? We have now our second motivation, and we want to start in a completely different way. First of all, in order to do that, you need to forget everything. In order to have a free mind. And then the only thing that we require now is that we have electron field psi of x, and we want to describe the electron field psi of x. Okay, and we know it's a complex field. It's also spinor valued, but that is not important now. It's complex, and so now we can do something similar to this geometric study here. Let us write down our space, Minkowski space of the x coordinates, and what it means to have a field is that at every point x, here or here and so on, there is a field defined. So here there is psi of x is defined here, and psi of x is complex. That means you need something like a coordinate system for your real and imaginary parts of the field. And so let me write this here in green. So we have some coordinate system. These are the coordinate axes for the real part and the imaginary part of our field psi of x. And then in this coordinate system, a complex number is like a vector. So for example, this vector here is now our field psi of x at this particular point, and the real part and imaginary part are measured according to the green axes. And the same is true at any other point. So here, for example, you have the field at position y, and you have also some coordinate system for the real part and the imaginary part, and the field is in this complex coordinate system some vector. And now, of course, having in mind the yellow discussion, you might wonder, is it actually automatically true that the coordinate system for the real and complex, real and imaginary part here and here, are they the same, or are they maybe different or independent? How do we know that? And so clearly we need to compare psi of x and psi of y, need comparable coordinate systems. For the real and imaginary part of psi. And that is necessary at every space-time point x. Okay. So this is an insight that you have after discussing the yellow geometric ideas. So now you would say, oh, okay, no problem at all, because clearly complex numbers are uniquely defined everywhere, and so there is nothing to worry about. And that is the naive point of view. And let me make that explicit. So far you would simply say, obviously, because you don't know any other reason to expect the contrary, obviously, clearly the coordinate systems are everywhere equal. Okay, that would be your answer. But what if they are not equal? What if that is actually wrong? And that is what we now assume. So now the change of mind is that we simply allow the possibility that actually, even though it might sound obvious, the complex coordinates for real part and imaginary part, they depend on x. So, and let us explore the consequences of allowing this possibility. If that is our starting point, then we end up.
طبعا هنا أنا أريد أن أذكر شيئا. هذا التشبيه، هذا التشبيه يتفق مع نظريتي تماما، لأن نظريتي أول شيء تتفق على أن هناك اختلاف من كل نقطة لنقطة في وسط التفاعل اللي هو في الانتراكشن ذاته. يعني قبل أن الجسيمات تبقى تصبح فري بارتيكل، المسؤول من ذلك هو معادلة تدفق المكان والزمان. فيقول أن الفيلد اللي هو الكومبلكس بالنسبة للفيلد اللي هو لا ساي وآي ساي أو ساي ريال وساي إيماجين، ذكر أنه تختلف هذا الاختلاف باختلاف إكس. أنا أقول أنه في نظريتي هذا الاختلاف في اختلاف معدلات تدفق المكان والزمان. إذن هناك اتفاق، هناك اتفاق. الاتفاق أنه في هناك يختلف، والاتفاق الآخر هو يختلف في الفترة الزمنية والمكانية. هو ذكر إكس يعني يعتبر الفترة المكانية. أيضا أنا أقول بمعدلات تدفق المكان والزمان، لكن أيضا معدلات تدفق المكان والزمان أيضا تؤثر في الفترة الزمنية والمكانية. لكن الفرق بيني وبينه أنه يقول يفترض أن إكس 3 أبعاد اللي هو طول عرض ارتفاع، أنا أقول 4 أبعاد مع اختلاف، وهذا مهم جدا. يعني حتى لو هو ذكر 4 أبعاد أنا أقول هي 4 أبعاد مع اختلاف بعد الزمان مع بعد المكان، لأنه رأينا في معادلات كثيرة خصوصا في مترية علي يوسف أن بعد الزمان يختلف من بعد المكان طبقا للكتلة، اللي هو المعادلة التي تخبرنا بالدي اكس على أو الدي ار على سي دي تي، فيها دالة لوغاريتمية والكتلة موجودة في المقام والحد الثاني الكتلة موجودة في البسط. هذه المعادلة المشهورة. فالكتلة تعمل على الاختلاف بين الزمان والمكان. هو سيفترض هنا أن فاي تتأثر فقط بإكس اللي هي إكس عبارة عن 4 أبعاد، وبالتالي سيجعل ال4 أبعاد متشابهة حسب معادلة مينكوفسكي، مترية مينكوفسكي. لكن الطريقة تقول لا، حتى الإكس والتي تختلف بعضها البعض، وهذا يظهر جليا في الكتلة. ولا يرى تطور الكتلة بهذا الفرضية، لا يرى تطور الكتلة. أنا بهذه الفرضية أرى تطور الكتلة، لأنه تطور الكتلة تلعب في معادلات تدفق المكان والزمان، وتجعل معادلات تدفق المكان والزمان مختلفة من بعض، أو تحاول أن تقاربها بحيث أن تجعل معادلات تدفق المكان يساوي معادلات تدفق الزمان، وبالتالي نظرية ترجع إلى معادلة مينكوفسكي لكن بشرط مقسومة ذلك أو محسوبا لصالح تضخم الكتلة. فالكتلة تتضخم من أجل إرجاع المكان والزمان ومن أجل إرجاع معادلة مينكوفسكي كما هي. فما يحمل هذا الاختلاف في التناظر هي الكتلة، لكن حول الكتلة التناظر يرجع كما هو، معادلة مينكوفسكي تطبق. يعني في الفضاء، في كوننا هذا الكون الفسيح الجميل، هذا الكون نحن نعلم أنه حسب السلسلة السابقة التي تقول النسبية العامة والنسبية العامة ولا علم الكونيات مقارنة بنظريتي، هذه السلسلة اثبتنا فيها أو رأينا فيها أن الكون هو مسطح. طيب، لكن ما لم نعرفه هو ما هو الذي يحمل هذا عدم تسطح الكون حسب النسبية العامة. أين تطبق النسبية العامة؟ وتطبق داخل الكتل وعلى حواف الكتل أو في الفضاء المحيط بالكتل وقريب منها. إذا معادلة مينكوفسكي تسيطر على الكون كله، والسبب هو أن الكتل هي التي تحمل عدم التناظر هذا، الكتل التي تحمل الانحناء، وبالتالي الانحناء ما هي الكتلة، ما هي الانحناء في الفضاء. ولهذا أنا في فيديو سابق ذكرت أن موجة شرودنجر بالنسبة للإلكترون والجسيمات الأولية تحمل انحناء في الفضاء، لأنه حينما وجد الإلكترون يحمل هذا الانحناء. هذا الانحناء سيكون خفيفا كلما تقدمنا نحو الإلكترون، وسيكون ضخما جدا داخل الإلكترون. هذا هو الانحناء. وبالتالي يعني نجد أن النسبية العامة تطبق حول الإلكترونات وداخل الإلكترونات. طيب، هناك يقول أن النسبية العامة تطبق في الكون كله، والدليل على ذلك هو معادلة فريدمان. هي تعتبر حل من الحلول النسبية العامة تطبق في الكون كله. نعم، هذا صحيح، لكن معادلة فريدمان أثبتت لنا شيء لم تستطيع هي تفسيره، وهي الطاقة المظلمة. الطاقة المظلمة هي من أجل محاولة أن جعل الكون مسطحا حسب نظريتي، فمعادلة فريدمان لم تستطيع تفسيره. الشيء الآخر الذي لم تستطيع تفسيره هي المادة المظلمة. فالمادة المظلمة هي خاصية أساسية من خواص اختلاف تدفق المكان والزمان، وهذا لن تجدوه في جميع النظريات الأخرى، لأنه أي نظرية لا تعتمد على أو لا تعترف باختلاف في معدلات تدفق المكان والزمان بالقرب من الكتل أو في الانحناء، فهذه نظرية لا تستطيع تفسير هذا الأمر، لأن القوى الأساسية الأربعة أو الثلاثة، القوى الأساسية الثلاث تتأثر بهذه المعدلات، الاختلاف في معدلات تدفق المكان والزمان. وبالتالي سنفترض في أي نظرية أخرى سنفترض أن القوى الأساسية الثلاثة ثابتة في جميع أنحاء الكون، لكن في الحقيقة هي لا. وهذا ما أظهر لنا المادة المظلمة أو تأثير المادة المظلمة. المادة المظلمة تعبر عن ذلك. فالقوى الأساسية الثلاثة تختفي عندما يكون الفرق كبيرا بين معدلات تدفق المكان والزمان، وتتقارب جدا عندما تكون وتظهر جليا هذه القوى الأساسية الثلاثة عندما يكون معدلات تدفق المكان والزمان متقاربة بعضها البعض. إذن نظريتي أوجدت حد إضافي. هذا الحد الإضافي لم يرى في النظريات السابقة، هو أن اختلاف معدلات تدفق المكان والزمان يصب في مصلحة أو تحاول أن تحاربه الكتلة والشحنة. الشحنة أيضا تدخل في هذا الأمر، الكتلة والشحنة، لكن الشحنة مرتبطة بالكتلة. ربما هذا ما يجعل الشحنة تختلف قليلا لأنها مرتبطة بالكتلة. أنا في الحقيقة أذكر هذا الكلام، أقول هذا الكلام لماذا؟ لأن هناك مشكلة الآن وجدتها في كتاب الحلقة 54 وأحاول تفنيدها، وهي المشكلة التي تتعلق ب degrees of freedom بالنسبة للQCD، والتي ظهرت في الصبغة اللونية أحمر وأخضر وأزرق. هذه الصبغة اللونية يجب أن نجد لها تفسيرا في واقع الفضاء، فضاءنا. لا يمكن أن تكون هي internal degrees of freedom، يجب أن تكون لها خاصية أساسية في الفضاء، أربع الأبعاد الذي نعرفه. وهذا ما وقفني حقيقة عن نشر كتابي، لكن سأحاول أن أمضي فيه قدما إن شاء الله، وسأنشره ثم بعد ذلك أطوره مرة أخرى عندما أتوصل لهذه النتيجة الخطيرة جدا جدا. نتيجة خطيرة جدا جدا هذه عندما أعبر عن الصبغة اللونية بدلالة الفضاء الذي نعرفه. هو عبارة عن 4 أبعاد من الفضاء، ومن قبله بعدين من الفضاء. هذا البعدين ولد منه 4 أبعاد من الفضاء، أو ولد منه بعدين آخرين. إذا نحن نتحدث عن 4 أبعاد في الفضاء: مكان، زمان، مكان، طول، عرض، ارتفاع، وزمان. وبالتالي يجب أن نترجم الصبغة اللونية أحمر، أخضر، أزرق في هذا الموضوع. إذا استطعنا نفعل ذلك فإننا لن نحتاج لما يسمى بالقولونات، فكل ما سنحتاج إليه هو أن التغير في هذا الفضاء الغريب هو الذي يصب في التغير في الكتلة. في الحقيقة أنا جاءتني فكرة الآن، فكرة خطيرة جدا جدا. بما أن الكتلة، بما أن الQED والQCD لا تحترم بالزمن، إذا لماذا لا تكون هذه degrees of freedom أحمر، أخضر، أزرق تعبر عن المكان فقط؟ لماذا لا نرى هذا الأمر؟ تعبر عن المكان فقط، بالرغم أن هي internal degrees of freedom لكنها تعبر عن المكان فقط. وهذا يجعلنا أن نفترض أن المكان يتغير، وهذا واضح أن المكان يتغير في نظريتي، بحيث أن طول، العرض، الارتفاع يتغير، لأنه هو عبارة عن بعد واحد بالإضافة لبعد الزمن. الأبعاد الثانية العرض والارتفاع خرجت من بعد الزمن، بعد المكان بسبب الكتلة. سأفكر في هذا الأمر حقيقة، سأفكر في هذا الأمر. طيب نرجع إلى نظريتي، إلى المحاضرة.
The following result, namely we need a mechanism, a mathematical mechanism to tell us how the different coordinate systems at different points are related. Similarly to here, we need the notion of a parallel transport. We need to say, for example, I can parallel transport this vector to a new point. but it's the same vector, but its coordinates have changed, and then I know how to compare that vector to this vector despite the different coordinate systems. So this is the outcome. So we need information to compare psi of x and psi of y, and that is
معليش أنا سأدون هذه الحقيقة أو هذه النتيجة التي توصلت إليها ثم أرجع لكم مرة أخرى لأنه النتيجة في غاية الأهمية صراحة.
That is the notion of a parallel transport in this different kind of geometry. And let us do it for an infinitesimal distance dx mu. So the variable dx mu denotes an infinitesimal distance, and let us now try to come up with a definition or a relationship for the parallel transport along such an infinitesimal distance. So here let's draw just a line, and at this line I have again here some coordinate system for real part and imaginary part. Here is a modified coordinate system for real part and imaginary part, and I want to parallel transport this vector, in other words the field psi of x, from this point to that point such that the field value physically remains the same, but possibly it's described with other coordinates. So then we have here the original field psi of x, and this parallel transported result I denote in the following way: psi parallel of x plus dx. This means that we take this original field value at the original point x, we parallel transport it along that distance and obtain this result. Okay. This is first of all the name symbolizing this parallel transport, and then we can write down an ansatz. And what are the properties that this ansatz should fulfill? First of all, how does the outcome depend on the original field psi? Remember that psi is a field which lives in a vector space. You can do linear combinations between different psi fields. You can do psi 1 plus psi 2. You can multiply psi with a scalar quantity 2 times psi and so on. And these linear combinations, they should survive parallel transport. So if you parallel transport a linear combination, the result should be the linear combination of the parallel transported results. And therefore this must be linear in the original psi of x. Therefore we know that if we write down an equation here, it will be linear in the original psi of x. Then it's also linear in the distance dx mu, because the distance is infinitesimal, and so whatever the change of the coordinate system might be, we assume it to be differentiable. And if it's differentiable, then of course the dependence on distances can be approximated by a Taylor expansion, and for infinitesimal distances only the linear term remains, and therefore we get something which is linear in this dx mu. At least the change. And by the way, so I should start here. First we get of course the original field, and then we get some correction term. The original field must be there, and then the correction term is infinitesimally small and linear in the dx mu. Okay, and the only thing that remains now to say is that the coefficient of this is now the object which defines what a parallel transport actually is. And so we can now write down a coefficient in front of this object defining the parallel transport, and that coefficient must apparently be something with a Lorentz index mu. So let us write down something with a Lorentz index mu, and of course it depends on x, because the parallel transport might be different at every x, and so let's write down just by convention minus IEQ as a prefactor, but the main thing is a mu of x. We need an object which is x dependent and carries a Lorentz index mu. And this object a mu, or with this arbitrarily chosen prefactor a mu, is the object which defines parallel transport along this infinitesimal distance.
طبعا بعدين سنكتشف الاي ميو ما هو الا الفوتون، لانه الفوتون او بوزون سبين 1 تحديدا، لانه السبين 1 هو الذي يتحمل الجيج، مش يتحمل، لديه في داخله الجيج انفاريانس او الجيج ترانسفورميشن، كما راينا في المحاضره الاولى، محاضرات الاوائل، حيث ان الكونسترينز تطبيقها الكلاس 1 الذي فيه الجيج انفاريانس او الجيج ترانسفورميشن اللي هو كلاس 1، ويطبق على السبين 1، والكلاس 2 طبعا لا يوجد فيه جيج ترانسفورميشن، والسبب انه لا يوجد فيها جيج ترانسفورميشن لانه المفترض انه طبعا الكلاس 2 فيه فيه اثنان من الكريتيريون او من الكونسترينز، هذه الاثنان مفترض ان طرحهما يساوي زيرو. إذا كان طرحهما الكونسترين الأول والكونسترين الثاني طرحهم يساوي زيرو، فهذا يعطينا ماذا؟ هذا يعطينا كلاس 1. إذا كان لا يساوي زيرو يعطينا كلاس 2. ولاحظ أن الكونسترينز هذا برضه أمر اكتشفته الآن. الكونسترينز كما ذكرنا عبارة عن الأول عبارة عن مشتقة للمكان يساوي زيرو، مشتقة للزمان يساوي زيرو، بحيث أنه فرضنا أن باي حتى يصبح كونسترين أن باي لا تعتمد على الزمان، وإنما تعتمد على المكان فقط. فبالتالي أي باي تعتمد على الزمان، يعني باي اللي هو المشتقة بالنسبة للأجراج بالنسبة ل كيو نوت أو مثلا فاي نوت، هذه المشتقة فاي نوت يعني تعتبر زمان، لو مشتقة الفاي بالنسبة للزمان، أو مشتقة الفاي بالنسبة للكل ليس الزمان. لكن من هنا نحن نعتبر أن المشتقة للزمان يساوي زيرو، والكونسترين الثاني أن المشتقة للمكان يساوي زيرو. هذا الكونسترينز، التو كونسترينز إذا طرحناهم من بعض وجعلنا القيمة زيرو، فهذا يعني أن يعتبر الكونسترينز هذه من كلاس 1. أما إذا كان لم تساوي زيرو فهو من كلاس 2. نجد أن الفايمان معادلات فايمان تعطينا كلاس 2، وكلاس 2 يعني أن هناك فرق بين المشتقات المكانية والزمنية، وهذا ما ذكرته الآن للتو، أن الكتلة تتحمل هذه الاشتقاق، وبالتالي الفرميون اللي هو سبين 2 السبين هاف يتحمل هذه الكونسترينز اللي هو الفرق بين المشتقات المكانية والزمنية يساوي زيرو. وهذا يعتبر شرط من شروط الجسيمات لكي تخرج من داخل التفاعل لخارج التفاعل، أن المشتقة للمكان والمشتقة للزمان يجب أن لا تساوي زيرو، وهذا ما تقوله نظريتي. هذا اكتشاف خطير جدا جدا، يا دوب اكتشفته الآن. أما في الكونسترين 1 الكلاس 1 فإن المشتقة فقط للزمان يساوي زيرو، ما في شيء آخر. يعني في الكلاس 1 الذي هو يعتبر جيج انفاريانس، وأن المشتقة للمكان للزمان يساوي زيرو، وبالطبع أن المشتقة للمكان يساوي زيرو، لكن الفرق بين المشتقة للمكان والمشتقة للزمان يساوي زيرو. لماذا؟ لأن الفوتون ليس لديه كتلة. طبعا سنقول الWZ لديها كتلة، هذا ما يجعلنا نظريتي تصحح النسبية، تصحح الQFT أن WZ هي ليست لديها كتلة وإنما طاقة صرفة لكن مكثفة جدا وطاقة تعتبر أضخم من طاقة الفوتون. طيب نرجع مرة أخرى فإن المشتق في حالة الفوتون الفرق بين مشتق المكان ومشتق الزمان يساوي زيرو فعلا لأنه الفوتون ليس لديه كتلة. أما في حالة الفيرميون فإن المشتق المكان ومشتق الزمان لا يساوي زيرو وهذا واضح أن الكتلة هي التي تحمل هذا الفرق بين المشتقات بين المكانية والزمانية. هذا كلام جميل جدا جدا في الحقيقة، كلام جميل جدا جدا اكتشفته للتو. طيب ماذا أفعل؟ تعال نواصل المحاضرة.
Of course, you know that this will be the photon field and the gauge field, but here it's not yet the gauge field. It is what we call a connection of x. We need an object which is x dependent and carries a Lorentz index mu. And this object a mu, or with this arbitrarily chosen prefactor a mu, is the object which defines parallel transport along this infinitesimal distance. Of course, you know that this will be the photon field and the gauge field, but here it's not yet the gauge field. It is what we call a connection. Mathematically, this is a connection which describes parallel transport in the coordinate system for the real or imaginary part of psi. Okay. So this is the meaning of a mu here in this formalism, in this geometric setup. And it is important to be able to compare fields at different space-time points. And at this point, let me point out the comparison to general relativity. In general relativity, maybe you know that the notion of parallel transport is also very important, and there you basically have curved geometry of space-time similar to the curved surface of a sphere. And in order to describe parallel transport there, you need so-called Christoffel symbols. So there, parallel transport of a 4-vector, for example, is defined. And it looks like as follows: v rho of x. So that would be a 4-vector defined at x. It's a 4-vector field. And it goes into the parallel row of x plus dx, which has the following relationship, namely equal to the original v rho of x, then minus a Christoffel symbol, gamma rho sigma mu of x times v sigma of x times bx mu. Okay. So this is the parallel transport, and you see it has the exactly same structure, namely it is linear in the original 4-vector. It is linear in the infinitesimal distance, bx mu, and there is a prefactor. The prefactor is basically here a matrix, rho sigma, in the space of 4 vectors. So you have here v rho goes to gamma rho sigma times v sigma matrix. But it has this additional index mu corresponding to the distance along which you want to do the parallel transport. And so this Christoffel symbol is, of course, exactly the analog to our gauge field a mu. is the precisely analogous object. And so in general relativity, you can do basically everything that follows. From now on, we will go on with discussing more formalism.
طبعا هذا ما عبرته بالضبط في كتاب الحلقة 50. كتاب الحلقة 50. تعالوا نشوف. بهذا الكتاب. هذا الكتاب عبرته بالضبط أن الكونكشن فيلد يعتبر حلقة الوصل بين عالمنا والعالم عالم التفاعلات الدون الذرية. كتاب حلقة 50 يتكلم عن adopting the WKB theory وبعدين الفيلد كونكشن. فيلد كونكشن الآن يذكره المحاضر and the covariant principle. هذا هو كتابي تحديدا يتحدث عن هذا الأمر. يمكنكم تحميله من ريسيرش جيت، موقع ريسيرش جيت، أو ممكن تحميله من أكاديمية فيديو، أو ممكن تحميله من يعني صفحتي سيامتيس علي يوسف، أو الجروب في الفيسبوك علي يوسف جروب أيضا موجود في هذا الجروب. وبعد ذلك لدي عناوين، إذا لم تجده في هذه المواقع لدي عناوين موجودة في هنا في البداية. هنا هذه عناوين يمكنكم الاتصال عليها لأي استفسارات أخرى ولا أي شيء تريدونه. هذا الكتاب يعبر عن هذا بكل وضوح. نرجع.
Discussing more formalism in this point of view, and everything that I will say about QED will have an exact analog in general relativity, where basically a mu gets translated into Christoffel symbols. So the next thing before I clean the blackboard would be the following. Since we now are able to compare fields at different points x, y, we can also do derivatives in a meaningful way, like what is the change, the physical change of the vector from here to here. It is not meaningful to take the difference of the coordinates between the two vectors because they are defined in different coordinate systems, but it is very meaningful to first parallel transport this vector here, and then both vectors are defined with the same coordinate system, and then you can take the difference, and that difference is physically meaningful. And let us define this difference as a sensible, physically meaningful derivative. So you have first here a vector, psi. I call it vector because it is a vector space object, psi of x. And here you have a new different vector, psi of y. You want to compare them in a physically meaningful way. Therefore, what you need to do first is to parallel transport this vector here. Then you get psi parallel at let's say y, which is the reflection of the original vector but parallel transported, and then this difference is physically meaningful. And we can formulate this as a derivative, which I call covariant derivative, and write with a capital D, d mu of psi of x is defined as the following limit, where the infinitesimal distance goes to 0, and we compare exactly those two objects, namely psi at x plus dx minus the parallel transported original psi parallel transported to x plus dx, and we divide by dx with a fixed index mu. And then we take the limit. That is the physically meaningful derivative. And so let us work out what that derivative actually is, because we can compute what it is. in terms of the connection field A mu, because the parallel transported psi is given here. It depends on the original psi, so let's plug it in here. So then you get psi of here, this psi at the shifted argument minus psi at the original argument, plus I eq times A mu times psi. So there is this additional term, and in the additional term, the dx mu appears in the numerator and in the denominator, so it just cancels. Therefore, we get the covariant derivative of psi of x is actually the normal derivative coming from this difference, normal derivative acting on psi of x, plus I eq times A mu of x. Right? So this is just a multiplicative factor. And the name of this object is covariant or gauge covariant derivative. And I highlight here that I will always use a convention where in the covariant derivative we have a relative plus b mu plus I eq a mu and so on. There are books which do it in the opposite way. So this
طبعا يمكن الشرح أيضا لماذا هو اختار الموجب ولماذا هناك كتب تختار الأوبجكت وير اللي هي السالب. الشرح كالآتي بسيط جدا، الشرح بسيط جدا حسب نظري. احنا نتكلم عن معدلات التدفق والمكان والزمان، أو ممكن نتكلم عن فترة زمنية والفترة المكانية بشيء جميل وسلس جدا. نجد أن دي ميو كابيتال يعتبر اشتقاق في أحد الفضائين، إما في الفضاء الكثيف الذي فيه الفضاء الكثيف الذي فيه معدلات التدفق عالية، والدي صغيرة هي عبارة عن الاشتقاق موجودة في فضاءنا نحن. مثلا إذا فعلنا ذلك فإن نجد أن الدي ميو كابيتال يجب أن تساوي الدي ميو سمول زايد. هذه زيادة جاءت من ماذا؟ زيادة جاءت أنه هناك معدلات عالية التدفق وهنا لا يوجد معدلات عالية التدفق، وبالتالي يجمع هذا إلى ذلك. طيب في حالة هذا في حالة الزايد، في حالة الناقص تختلف الآية، لأن الدي كابيتال ستكون هي فضاءنا نحن، والدي سمول ستكون هي الفضاء الكثيف، وبالتالي سيكون ناقص. فالموضوع بسيط جدا جدا، يختلف عن يعني يعبر عن ما نراه ما هو المناسب في ذلك.
This is now our gauge covariant derivative, which of course has an analog in general relativity as well. Next, we want to look at a few properties of this, like properties under coordinate transformations, in other words, under gauge transformations. Namely, under a change of the coordinate system. I write coordinate system in quotation marks because, I mean, it's a little bit artificial to speak of a coordinate system for real and imaginary parts, but that's what we mean. And the other word would be gauge transformation. So under such a coordinate transformation, the field psi of x goes now into a phase transformed field, because at every point I can do a new coordinate system for real and imaginary parts. That means the coordinates of the field at x change like this. They change by a phase. At every x I allow a different change of phases of the complex value of psi, and the phase change is defined by this alpha of x function. And again I put here this arbitrary normalization prefactor, but this just defines an arbitrary phase rotation which can be done independently at every space-time point. And the outcome would be called psi prime of x. So if we go from an original coordinate system to a changed coordinate system, where the change is local and x-dependent. So then we have an original system for psi, and we have a primed system for psi prime. And let me draw some pictures and then draw hopefully some clear conclusions. So in the coordinate system for psi, you have here psi of x, and here the parallel transported psi parallel of x plus dx. Psi of x is parallel transported to pi parallel at a shifted position. And we know how they are related, namely in terms of the gauge field. Okay, it is deleted, but the difference is given by minus IEQ times A mu times psi and times dx. So we know how they are related, and now let's draw the same thing in the primed system. The physical vectors, in other words, the physical fields remain the same. They are only described in terms of different coordinates. So let me write down the coordinates. So first of all, here we had, let's say, this coordinate system, and at the shifted position, we already had a different coordinate system. So here you see the angles of real and imaginary parts are slightly different. That is why we have a non-trivial parallel transport from here to here. And now we do a phase rotation at every point. That means in the primed system, this coordinate system is completely changed. For example, it looks like this. And that is also completely changed, and maybe it looks like that. Okay? But the physical vectors always remain the same, but they are described in 4 different coordinate systems. And then here we have psi prime of x is the coordinate of this vector in that coordinate system, and here psi prime parallel of x plus dx are the coordinates of the parallel transported vector in this frame. And now we can learn something about the parallel transport in the new frame compared to the parallel transport in the old frame, because those two are related by parallel transport with A mu, and those are related by a new parallel transport, let's say A prime mu, in the prime coordinate system. And by comparing the pictures, we can learn what this A prime mu actually is. And that is what I want to calculate. So let's write it down first. So this is given by psi prime of x minus IEQ A prime mu of x times psi prime of x dx mu. And this is given by the similar relation without primes. And so this defines parallel transport in psi prime system. Okay, A prime mu, that must exist. But now we also can plug in that this is actually equal to e to the minus IEQ alpha of x times the original psi of x, right? Because that was our coordinate transformation. And this here, we also know what that is, because on the one hand it's this, but on the other hand it is also the transformation of the coordinate system from the original parallel transported field. So this is given by that e to the minus I eq times alpha at x plus dx times the parallel transported original field. All right. And now we have a system of equations. On the one hand, this field here, the coordinate values, can be obtained by starting from here and applying parallel transport with A prime. On the other hand, it can be obtained from here by applying the coordinate transformation, which is this relationship. And of course, the result must be the same. Therefore, we can equate the two, and by equating the two, we get the relationship between A prime and the original A. And that is what we want to know. And then we know how parallel transports are related after coordinate system changes. And what is the result? The result is that A mu must be replaced by a new primed connection field, which is given by the original connection field plus B mu alpha of x. A non-surprising result. But you can easily check it. We do not need to put in many details of the calculations, but you see that plugging in this by parallel gives rise to the original A mu connection field. But that is combined with alpha at the shifted position, and from this there arises a derivative, alpha derivative with respect to x mu times dx mu. And that is the difference, and therefore the primed A mu is the original A plus this derivative of alpha. This comes exactly from this shift in the phase rotation here. So you should just plug in all the symbols, all the definitions, then this is immediately possible to read off this transformation rule. Okay, and the result is of course not surprising. It is the usual gauge transformation of A mu. But it comes out here from a purely geometric perspective. We want general coordinate system transformations, and we need parallel transport, and the parallel transport connection field has this behavior under coordinate transformations. And again, there is an analog relationship for the Christoffel symbols. So we have now the transformation of the field psi of x. We have the transformation of A mu, and we have a definition of the covariant derivative. Now we want to determine what is the gauge transformation of the covariant derivative. Let us write this down here as well. Namely d mu psi of x. How does this transform actually? If you plug in everything, then d mu psi acting on the phase rotation. So this derivative here acting on the transformed field gives you a derivative of alpha, and the shift in A mu gives you also a derivative in alpha. The two derivatives of alpha cancel between themselves, and therefore the transformation rule is simply this, that the covariant derivatives transform covariantly, namely with a phase. That is the simple transformation rule of covariant derivatives. Do you want to see this calculation explicitly? This is the standard calculation that you have done certainly in other lectures. But let me know if you want to see it. It's fine to write it down. But since that is total standard, I would only write it down if you ask me. But you don't ask me. But do it at home, plug in all the values for all the fields and really rederive that for yourself. It's a two-line computation to fill the blackboard with all the symbols, and then you can read this off immediately and you can satisfy your curiosity. Okay, so now what do we have? We have a geometry where at each space-time point we have a different definition of real and imaginary parts for the complex phases of our field. We can do local phase transformations, in other words, gauge transformations. In every coordinate system there is a connection field, a mu of x, similar to Christoffel symbols. We can transform the field from one coordinate system to the next. We can do it for a mu, for psi, and also for the covariant derivative. That is a nice geometric setup, and now we can start doing physics in this geometric setup with such locally transforming complex phases. Physics in this geometry. So we want dynamics. That means we want to write down a Lagrangian, and the Lagrangian should be invariant under this change in coordinate systems, because we simply say physics is independent of the description in terms of arbitrary coordinates. Therefore, we want to write down an action, at least, or a Lagrangian, which is independent of that reference frame. Such coordinate transformations, in quotation marks, because I'm talking about the coordinate system for real and imaginary parts. In other words, I'm talking about gauge invariants. And the gauge invariant Lagrangian is then obviously this, where we simply have a derivative term which contains the covariant derivative, because now the covariant derivative transforms covariantly under those local gauge transformations, and because of that psi bar transforms with the opposite phase, and so the local phase transformations simply cancel. And so this is an obvious, simplest locally gauge invariant Lagrangian, which describes a free electron. It contains, of course, the free electron Lagrangian, but it is modified in such a way that it is invariant under these local phase transformations. So what is the physical meaning of this Lagrangian? Remember that we started out, our starting point was simply to say we have an electron field, nothing else. Now we have introduced geometry, we have geometric objects like this connection field A mu. And this has only a geometric meaning. It is only there in order to allow these changing coordinate systems, and so, but we still really physically have only the electron field here at our disposal, and somehow the Lagrangian contains, of course, this gauge field. And so this first of all describes dynamics of the field psi. And if it happens to be that the connection field A mu vanishes identically everywhere, why not? Then of course we have here the free Lagrangian for the free electron. So then psi is simply a free field. And so now we are back to the beginning example where I wrote down the plane, the two-dimensional plane in yellow, where I said, okay, we can define vectors on the plane. We can describe the vectors in polar coordinates, but we could just as well describe them in Cartesian coordinates. Then the description is, of course, trivial. So here the same. We might have a free electron field, which we can describe in this obvious coordinate system where the phases are defined everywhere in the same way. Then we do not need this connection. A mu vanishes identically, and then we have just a free electron. But okay, that's all right. But now we have the possibility to describe the same thing, the free electron, by going to an arbitrarily complicated, locally changing reference frame for the complex phases. And the changing complex phases are taken into account by this connection field A mu. But the physics is the same as before. We just describe it in a randomly complicated coordinate system. So then, of course, this Lagrangian still describes the free electron, just in a more complicated way. Think of the Coriolis force in classical mechanics. You have a simple thing, but you describe it in a rotating frame or whatever, and therefore the equations of motion look complicated, but it's still the same physics as before. And so maybe the same thing happens here. So that means if you have some non-zero A mu, you know that the phases depend on x. You have a complicated situation. But maybe you can actually go back by choosing a clever coordinate transformation. You can go back to a coordinate system where the A mu vanishes identically. And then you know that your physics is actually free. Therefore, a good question, a physics question now, is the following. Suppose you start out with a situation where the field is non-zero and you have these fluctuating phases. Then are you able to find a coordinate transformation which is such that afterwards the A mu is identically zero? That is a good question. And so we should try to answer that question. Let me write it down. Can we always find new coordinates? Coordinates in quotation marks, because this really an
طبعا في نظريتي هذا ممكن أن يكون نجد كوردينات A يساوي زيرو. ما هو الكوردينات الذي نحن فيه؟ يعني الكوردينات الذي نحن فيه A يساوي زيرو، لأنه A أصلا خارج من فضاء كثيف، فقط ما نحتاجه هو فضاء ليس كثيف مشابه تماما الفضاء الذي نحن فيه، وبالتالي A ستساوي زيرو. الموضوع بسيط جدا بالنسبة لي. لهذه A تعتبر طاقة مطرودة من التفاعل. A تعتبر طاقة مطرودة من التفاعل، وبالتالي إذا ساوينا بين ذلك الفضاء الكثيف وفضاءنا نحن، فإن الطاقات التي هي مطرودة من التفاعل لن تكون مطرودة بعد ذلك، لأن الفضاء ثنائي الأبعاد يعني استطاع أن يدبر الأمر، واستطاع أن يمحو تهديد الطاقة العالية والكتلة العالية، وهذا موجود في فضاءنا. نحن فضاءنا مستقر الآن، نجد أن فضاءنا نحن مستقر. يعني الفضاء الذي على الأرض هو فضاء مستقر، لا يتغير هذا الفضاء. يعني أنت الآن في السودان مثلا تريد أن تذهب إلى مصر، هل ستجد صعوبة في ذلك؟ هل الفضاء سيتغير؟ هل أنك تتضخم أو تضعف، أو أنك ستجد صعوبة في اختراق جدار عازل كبير جدا ستجده في الحدود بين السودان ومصر؟ لا، ليس هذا زي ما تجده، إنما ستركب الطائرة وستذهب بكل أريحية إلى مصر. فإذا الفضاء نحن فضاء مستقر، فضاء خلاص، الفضاء ثنائي الأبعاد سيطر عليه، والآن نحن نأكل ونشرب فيه ونمارس أنشطتنا بكل أريحية. لكن عند التهديد الفضاء اللي هو عند الكتلة العالية والطاقات العالية، فإن الفضاء ثنائي الأبعاد لن يكون مستقرا، وبالتالي هنا سيظهر المشاكل، وهنا سيظهر التغيرات التي تحصل في الكتلة.
Imaginary coordinates where A mu vanishes identically everywhere. That is now the question. And let me just explain once again. If the answer is yes, then this Lagrangian simply describes the free electron, but in a complicated way. Whether we can always find such a coordinate frame is a geometric question. It's a geometric question, and so we must now continue analyzing the geometry that we have set up here, and we will analyze whether and under what conditions it is possible to set it to 0. And what could the answer be, and what is it related to? It is related to the two examples from the beginning in yellow, namely consider either the plane with polar coordinates or the sphere where you have locally Cartesian coordinates but not globally. So this is exactly the comparison. And so from these two examples you see that in the geometric case, clearly sometimes you are able to find globally Cartesian coordinates where parallel transport is trivial everywhere, but sometimes, like on the sphere, it's not possible. And then no matter what you do, you will always need to define parallel transport in a complicated way, adapted to the geometry that you have. And so let us see what that means here. That is our next section for 1.3. Still doing motivation 2, but now looking at a concept called curvature. So the question that we investigate is this one: can we find a globally trivial coordinate system? And that is not always possible, and there is a possible geometric obstruction to this. And in order to see this, we do a parallel transport along a closed loop. Or maybe simpler speaking, we go from x to y in two different ways. We go from x to y either in this way, by first going via dx, we go to x plus dx, and then we go into dy, and we go to x plus dx plus dy. Or let's call it path 1 and path 2. We do a parallel transport along this set of paths, or we do the opposite. We first go here, let's say path 3 to x plus dy, and then we go here with path number 4. We arrive at the same final point, but we do the parallel transport along two different lines, and we will discuss at the end that if the outcome is different, then this corresponds first of all to curvature, and second of all it provides an obstruction, and we will prove that in this case it is not possible to globally set a mu to 0. That will be the outcome, but let us analyze this situation, and then we will see what I claim. So, in short words, what we want to do, our goal is to compare psi parallel transported along the path 1, 2 at x plus dx plus dy compared to psi parallel along path 3 and 4 at the same final point. That is our goal. So I think the time will be sufficient to write down the appropriate formulas. So what is the final outcome if we go along path 1 and 2 in a two-step procedure to x plus dx plus dy? So it's a two-step procedure, therefore we need a few calculational steps, but I can, on the left-hand side of the equation, I can immediately write down the final outcome, and we now have to calculate it step by step. This final outcome, if we go in this order, we want to end up here, so we go backwards. We must come from there and use parallel transport from this point to here in order to obtain this. Okay, and so the first step is to write down the parallel transport of that object to the final place. And so we need to start with the object which is defined at this position, that is the parallel transported psi at x plus dx, right? This is the field at this point after parallel transport along path 1. And we will be able to write down what it is, but let's first write it as a symbol, and then do the parallel transport to the final position, and that is minus I eq a mu at this point, x plus dx, times the field psi parallel at x plus dx times dy, and sorry, let me use Lorentz index nu here, dy nu. Okay. So that is literally copied from the original definition. We have a field defined at this point. We do parallel transport along dy and write down literally all the symbols. But we have here some complication because the coordinate is x plus dx. And the shift is dy. But that's nothing new. But now we can plug in actually the value of psi parallel at x plus dx, and that is literally what we always wrote down before. So let's plug it in. So let me write it explicitly for this case, psi of x minus I eq now a mu at x times psi of x times dx mu. Okay, so this is that. And the same expression I need to plug in at this point as well. I need to plug in the same expression also at that point. And this here I can expand at first order in dx, because dx is infinitesimal. Then I get a nu at x plus derivative of a nu with respect to x times dx nu. That is also something I get. Okay, so maybe let us invest the time to write it down explicitly, or is it too obvious? It's not too obvious. Okay, so but then the blackboard will be a little full. Minus I eq times. So a nu at x plus dx is a nu at x plus derivative with respect to x mu of a nu at x times dx mu. Okay? Taylor expansion at first order in dx mu of that quantity. Agreed? So step by step. Very boring, but step by step. Next factor, psi parallel. I copy the expression from here. Psi parallel is psi of x minus I eq a mu of x psi of x dx mu. And then the whole thing is multiplied with dy nu. So there are too many terms there. Some terms can be neglected. For example, here there is a squared term of dx times dx that is negligible, so we will throw it away. We will work at most up to the order dx times dy, bilinear in dx times dy, but dx square we will throw away. So dx square drops out, and then we have terms which are of zeroth order in the dx's and dy's, zeroth order terms, first order terms, second order terms. And let us write down now all the terms. So first the zero order term, psi of x, and here another, there is no other zero order term, so this is the only zero order term. Then the first order term, where are first order terms? Here is a first order term, minus I eq a mu, and if I drop the argument, it's x. Let me drop the argument if it's just x, that times dx mu, this is a first order term. Any other first order terms? So here there is dy, the whole thing is multiplied by dy, But is there a term which is only dy and nothing else? No dx. No. That. Okay. Let me copy it. Minus I eq a nu times psi times dy nu. Okay. As simple as that. This is the term arising from these factors here. Now, second order terms. Second order terms, but only dx times dy. So there is a term dx times 0th order times dy, and another term 0th order times dx times dy. So there are two terms of the order dxy, dx mu times dy mu. Two terms like this. What is the result of the two terms? Let's say plus. And this term has minus I eq square, because one factor from here and one factor from there. And then there is a term as follows. So first we have this here, d mu a nu, that is this, times the first order term times the 0th order term, times psi. Let me write the psi here. Sorry, I think it's wrong. Actually, sorry. That's a mistake. So this factor cannot be factored out. Sorry about that. So let's start all over again. What is the second order term? dx mu dy nu. Second order term, one factor is definitely minus I eq, that is in front of everything else, and then we have a big square bracket. Any other factors which are common? Another factor which is common is psi. Let's factor out psi out of the square bracket, and then, so second order term, this times that gives simply d mu a nu times psi times the rest. Then that factor times this is the following: minus I eq times a nu a mu. That's it. Okay. That is the full term. And now we write, that is what we must do today. We write below it the analogous result if we do the other paths. If we do the other two paths, what is the difference? Also, we do not go through the details, but what is the difference? You swap x and y. Where do we swap it? So let me write down the result immediately by swapping at the right places. So here, for example, just x and y are swapped, but actually both terms exist anyway. Therefore, if we swap them, we get the same. And I will write it in the same order. Okay. What happens here? If we swap the paths, we swap dx and dy, but what happens precisely to the prefactor of this dx dy term? Yes, mu and nu swap in the bracket. So we get here d nu a mu minus I eq a mu a nu, and everything else is the same. Okay. So, and now we can stop, but we will continue on Thursday. And what is interesting is, of course, to look at the difference. We look at the difference and ask whether the two parallel transports give the same answer, and they might, but the difference is here. Here there is a difference in the bilinear term, and the difference comes from those different indices here, and we will discuss what that means, but maybe you see it already, that the difference here corresponds to the field strength tensor of QED. And so the field strength tensor corresponds to the curvature of this internal coordinate system corresponding to the complex phases. And so this curvature described by the field strength tensor is the physical thing that distinguishes whether we can globally find a trivial coordinate system where the connection field vanishes or not. And so curvature or field strength is physical, and that will be the result of this little calculation here, and we will summarize the outcome and discuss it on Thursday. Let us continue with our lecture from Tuesday. We were at the point where we introduced the so-called curvature on our internal system of coordinates, this kind of coordinate system for the real part or imaginary part of the complex field psi. And we studied the parallel transport along two different paths leading from one point to another point, and we can either go into this set of paths or along the other set of paths. And we discussed explicitly what happens if we do the parallel transport of a field from here, first to that point and then to the final point, or going the other way. And now I will not copy the results from the last blackboard that we had, but I will write down immediately the difference between the two results, which is the interesting quantity. In other words, we ask, is the parallel transport independent of the actual path, and does it depend only on the initial and final point, or is there a dependence on the paths themselves? And that is described by the difference, and the difference is written here. It just is obtained by taking the difference of the last two lines of the previous blackboard, and here you have it. That is the difference, and the important quantity is the square bracket here, which is literally copied from before. And what we have here is the so-called field strength tensor. So the field strength tensor tells us whether we have an independence of the actual path or not. And if that thing in the square bracket is non-zero, then we have here a non-zero difference, and that is the result of this analysis here. I have the impression that you have some questions to this, or not? Yeah?
We're thinking of the brackets and square brackets.
Actually, the round bracket here is zero. In our case of quantum electrodynamics, we are at the moment on the classical level, and therefore the round bracket is indeed zero, but it's a remark that I will write down also later. The remark is that, of course, one can do the entire analysis that we did literally with no change whatsoever for a so-called non-abelian theory, where the field psi is not only a spinor, but a column of different spinors, of several spinors, and the A then is a matrix. And then the two A's are different matrices which might not commute. And then this is literally exactly the same expression here, but with matrices, and then the round bracket might not commute. And so then you have here already the correct result for so-called general non-abelian Yang-Mills theories. But we applied only for QED, but the result is literally correct. Okay, and therefore the square bracket is an important quantity which tells us this path independence of parallel transport, and the name is so-called curvature. So what we are having here is curvature of this intrinsic coordinate system, and therefore we define now a name for this object, which is the field strength tensor in physical terms, but in our language now that is a curvature tensor, F mu nu, and it is defined by that d mu a nu minus d nu a mu plus I eq times the round bracket, which is zero here, but I write it down anyway. And let us immediately note that that can be written in a much nicer and more appealing form, which is also easier to generalize. Namely, this is actually a commutator between two covariant derivatives, where one covariant derivative is again given by that object. If you take the commutator of two covariant derivatives, you reproduce exactly the upper line. On the one hand, commutator between derivative and a mu gives this antisymmetric combination, and the commutator between two a's gives the round bracket, which vanishes here in QED. That is the so-called curvature tensor. And both definitions remain correct also for the non-abelian case. So-called Young-Mills theories.
بالمناسبة أنا نظريتي أو كتابي أو مشكلتي يمكن تحل في هذا السياق بالمناسبة. هذا موضوع جميل جدا جدا، يمكن أن تحل في هذا السياق، لأنه الاف مينيو اللي هو السترينجز تنسور هو عبارة عن كيرفيتشر. الله أكبر الله أكبر، صدق الحق. الاف مينيو هو عبارة عن تنسور، عبارة عن كيرفيتشر، ونعلم أن في الأبعاد الصغيرة جدا فإن الأشياء تتضخم، بالتالي الكيرفيتشر يزيد. الأشياء مثل عندما نتحدث عن الكوارك والتفاعلات الكوارك ولا القوى السترونج فورس والصبغة اللونية، طبعا دي زيادة degrees of freedom، وزيادة degrees of freedom يصب في مصلحة أو يأتي من تضخم الكتلة وتضخم الجاذبية. زيادة الجاذبية يعني زيادة degrees of freedom، أو زيادة الكتلة يعني زيادة degrees of freedom، وبالتالي نجد أن الإف ميو تعبر عن هذه الزيادة. إذن الإف ميو يمكن التعبير عنها بواسطة الصبغة اللونية الثلاثة. يعني طبعا الصبغة اللونية عاملة لي إشكالية كبيرة، لأنها فصلت لي الفضاء الداخلي من الفضاء الخارجي، فصلت لي القوة اللونية، القوة السترونج فورس أو القوة اللونية من الفضاء الخارجي. أصبح لدي فضاءين، فضاء داخلي وفضاء خارجي، وهذا لا يمكن. الفضاء متصل في جميع الأنحاء، الفضاء متصل. إذا حاول أن الفضاء ينقطع فإن الفضاء ثنائي الأبعاد مباشرة يفعل آليته للدفاع النفسي. إذا الفضاء متصل، لا يمكن الفضاء ينقطع، حتى لو الفضاء داخل الثقب الأسود وخارج الثقب الأسود الفضاء متصل لا منقطع، الفضاء متصل. وهذا يعني أنه القوة اللونية اللي هو أخضر أحمر أزرق ما هي إلا تعبير مشوه للتغيرات التي تحصل في هذا الفضاء المتصل، تعبير مشوه لهذا الفضاء المتصل. وبالتالي الديجريز اوف فريدم، النتيجة التي كتبتها في المرة السابقة يعني قبل قليل، النتيجة المهمة أن الأحمر والأخضر والأزرق يعبران لنا عن طول والعرض والارتفاع. هنا أستطيع أن أقول أنه لن يعبر عن الطول والعرض والارتفاع فقط، وإنما التأثير الطول والعرض والارتفاع على الإف ميو، تأثير على الإف ميو. طيب إذا هنا أنا محتاج أكون معادلة تحتوي على الإف ميو وكيف أنها تتغير بالطول والعرض والارتفاع. طيب واحد سيقول لي أن طول عرض الارتفاع متساوية لأنه الكتلة شكلها واحد. أقول لك أن الكتلة ليست شكلها واحد وليست متساوية، لأنه الكتلة تختلف. والدليل على ذلك ما هو؟ ما يسبب الأيز سبين. الأيز سبين يعطينا فروقات قليلة جدا بين الصاي وصاي والكونجيجيت. يعني مثلا في البروتون والنيوترون هناك فروقات بسيطة جدا في الكتلة، ناهيك عن الفروقات في الشحنة. في الكتلة هناك فروقات قليلة جدا، وحتى أنه ربما في السبين يكون هناك فروقات، حيث هذا سبين موجب هذا سبين سالب. نجد أن في الدبلت اللي هو دبل جنريشن نجد أن الأب والداون تختلفان في الشحنة، هذا موجب هذا سالب. وتختلفان أيضا في قيمة الشحنة. هذا موجب 3 على 2 على 3 وهذه تلت سالب تلت. وأيضا تختلف في الكتلة، الأب 3 فاصل حاجة وتلك والداون 4 فاصل حاجة. طيب يظهر هذا الاختلاف جليا في السكند جنريشن اللي هو بين الشارم والسترينج. الشارم أيضا لديه موجب 2 على 3 وكتلة الشحنة، والسترينج سالب 2 سالب تلت. هذا موحد، شحنة موحدة، لكن نجد أن الكتلة اختلفت كثيرا والإثبير أيضا اختلف، يعني أيضا عكس بعض لكن هو واحد، الاثنين نص نص، لكن هذا موجب وهذا سالب، لكن الكتلة اختلفت كثيرا. الشارم كتلته 1 جيجا فاصل 200 1.2 جيجا. الاسترينج كتلته 100 وشوية ميجا، 106 139 لا أعلم، لكن 100 وقليل ميجا. انظروا الفرق تحملته الكتلة. نجي السير جنريشن اللي هو التوب والبوتوم. أيضا الشحنة موجب 2 على 3 وهذا سالب تلت. وأيضا السبين موجب وسالب ونص نص. وأيضا نجد شيء الكتلة اختلفت كثيرا. الطب 172 أو 172 جيجا، والبوتوم 4 جيجا. يعني انظر إلى الكتلة أين ذهبت، مشت بعيد جدا وأصبح في اختلاف كبير. إذن هناك أشياء متشابهة، هناك أشياء مختلفة. من يتحمل هذه الأشياء؟ طبعا هذا ناتج من اختلافات الطول والعرض والارتفاع، لكن هذه الاختلافات ليست كاملة، إنما هناك من يتحمل هذه الاختلافات. من يتحملها؟ يعني الاختلافات ليست كاملة وإنما جزء منها، لكن احنا هنا فرضنا شيء، فرضنا أن الاختلاف في الأيسوسبين واحد، أو في السبين اختلاف ثابت، والاختلاف في الشحنة ثابت. هذا موجب 2 على 3 وهذا سالب تلت ثابت على طول الجنريشنز. لكن الاختلاف أصبح فري وأصبحنا لا نستطيع أن نتحكم فيه هو الكتلة. أصبح هناك اختلاف لا نستطيع أن نتحكم فيه، وبالتالي نستطيع أن نعبر عن القوى اللونية أحمر وأخضر وأصفر، أحمر وأخضر وأزرق، بهذا الاختلاف في الأبعاد الثلاثة طول عرض ارتفاع، لكن هذا الاختلاف مضروبة في الإف ميو. هذا تطور جميل جدا في نظريتي. ربما كتابي الحلقة 54 ربما أدون فيه هذا، أو ربما أنشره بهيئته الحالية لأبحث عن حلول لهذه المعضلة وأكتبها في كتاب آخر. هذا ما ستخبرنا به بقية الأيام، يعني اليوم ويوم غد إن شاء الله. تخبرها يعني سنعرف، لأنه أنا الآن انتهيت من كتابي، ووقفت لي نقاط يمكن في هذه النقاط يمكن أن أعبر عن عدم مقدرتي لحلها، ويمكن أن أضع هذه النقاط التي قلتها ذكرتها الآن أنني سأبحث في كتاب القادم عن حل التغيرات التي تحصل للإف ميو نتيجة للتغيرات التي تحصل في الطول على الارتفاع. جميل هذا التقدم جميل جدا جدا. سنذهب ونستمر في المحاضرة.
Just as a remark. And so then we can of course write this parallel transport around the closed loop, or the difference between the two paths, as a prefactor times this field strength tensor or curvature tensor times that object. So you see, the mismatch that you obtain by going through a closed loop in parallel transport is first of all proportional to the curvature tensor. If the curvature is 0, then there is no mismatch. If the curvature is non-zero, there is a mismatch. And otherwise, it is linear in the initial expression, because linear combinations always survive parallel transport. And then it is proportional basically to the area that is enclosed by the loop. So that is kind of the area that is enclosed by the loop. So this is all intuitively understandable. Okay, so this is really the mismatch. Okay, and now we have set up a formalism with intuitive insight into some new objects, geometrical objects and geometrical interpretations of objects. We have introduced parallel transport of spinors or complex fields along paths. We have introduced covariant derivatives. The parallel transport and covariant derivatives depend on this connection field, A mu, which is the gauge field. And around closed loops, we might get a mismatch which corresponds to this internal curvature, which is obtained by the commutator of two covariant derivatives. Now we can go back to the initial question that we asked at the beginning of this section, which was actually, is it automatically true or obvious that this coordinate system for the real part and imaginary part of a complex field is the same at every space-time point? That was our initial intuitive question, and naively we would say, of course, yes, it is. But now we can answer this precisely. Namely, the question really is a deeper question. The question is, do we allow for curvature in our intrinsic coordinate system, or do we not allow for curvature in our intrinsic coordinate system? It's our decision to either allow it or not in our theory, because we are theorists and we define what theory we are looking at. So we can either look at a theory that does not allow curvature. In that case, we can always go back to the case where there is no A mu field. We can set it to 0 by doing a coordinate transformation. Then there is no A mu and no curvature. And then that means we are in this naive situation where the complex coordinate system is everywhere the same. But we might now decide to allow curvature. Then F mu nu is non-zero. And if F mu nu is non-zero, then of course A mu must be non-zero as well. Otherwise, that cannot be non-zero. So then we must have parallel transport being non-trivial, and we must have non-trivial covariant derivatives in our theory. So that is now our choice, and therefore we can decide to either look at theories with or without this feature and discuss them. Before going there, let me write down another remark, which I forgot to make. What happens if we do a coordinate system transformation? Coordinate system change, where we do basically a gauge transformation of the psi and of the A mu. This object here, as a commutator of two covariant derivatives, behaves in a covariant way. So in QED, where that is 0, it's immediately well known to you that F mu nu is gauge invariant. So it's invariant under that coordinate change. And in a non-abelian case, it is covariant. That means it transforms in terms of a product. It transforms with an overall factor. So that is just a remark, and this is obvious here. So now let me discuss and write down the answer to the question from the beginning. So the question was, is the coordinate system obviously everywhere the same? So it's anyway a vague question, and that is always the point. Vague questions are good to develop intuition, but you cannot require a very precise answer to a very vague question. But now we have a pool, a formalism and a language and an understanding to formulate the question more precisely, which is, do we allow curvature in our theory or not? That is the precise question. And we might decide yes or no. So, and of course, if a mu is identically 0, or at least we can always find a transformed A prime mu after some coordinate transformation which vanishes identically. In both cases, there is no curvature. F mu nu is identically 0, and the coordinate system can be assumed to be everywhere the same. Let's say to be trivial. That's what I mean by this. But if we now allow for curvature, then we cannot get rid of the A. If, however, F mu nu non-zero is allowed, then we must use the formalism with A mu connection field covariant derivative and curvature tensor F mu nu. So that is the outcome of that analysis. And so now, of course, we are at this point. We will now postulate that we want to look at theories which allow this curvature, and then we want to study such theories because they look theoretically appealing, and we want to explore the physical consequences of this possibility. So let us postulate the following idea. We allow curvature and explore its consequences. Very good. Once we allow curvature, we have still two options. Namely, you could say the curvature just exists in the background. It comes from, we don't know where it comes from, but it is just there. We have to deal with it, and we have to describe physics of our psi field on this curved geometry. And we want to explore the physics of psi on a curved geometry with non-zero F mu nu. That basically means, in physical terms, that we provide from the beginning some classical background electromagnetic field F mu nu, which is somehow non-zero, and we want to describe the physics, maybe quantum physics, of a psi field on that background electromagnetic field. That is a nice field of study and a nice idea. However, there is the other option, namely we could also say the curvature itself is dynamical. There is some dynamics which governs the curvature, and the curvature is not fixed in the background, but it reacts to external influences itself. In other words, the curvature becomes a dynamical variable of our theory, of our system, and there are equations of motion for curvature and so on. And for us, in field theory, that simply means the action, the Lagrangian, should depend on the curvature. And then there will be equations of motions for it. So that is the next question. is the curvature fixed in the background. In that case, we can do quantum field theory with 4 psi with background electromagnetic fields, or the curvature is dynamical. So that is the next question, and of course we can define what theory we want to look at, and we want to look at a non-trivial case where the curvature is actually dynamical. So we write down another idea or postulate, namely curvature is dynamical physical quantity. So the action and the Lagrangian should depend on it. And then we can ask, what is the simplest theory which combines all those ideas, namely a theory which first of all contains a complex field psi, but that complex coordinate system allows this curvature that we have discussed, and therefore the Lagrangian also depends on the curvature, and the curvature is dynamical. So what is the simplest Lagrangian that we can write down, which combines that idea that will now follow? So the simplest Lagrangian is of course the Lagrangian of QED. Namely, it is first of all a Lagrangian which depends on our complex field psi. From the beginning we assume this is a Dirac spinor, therefore it's a Dirac spinor, so we have to write down something Lorentz invariant for the Dirac spinor. And initially that was the Dirac Lagrangian where we had a partial derivative here, but now partial derivative is meaningless. In order to have a meaningful derivative on this curved space, internal space, we need a covariant derivative. Therefore we need I d slash with a covariant derivative d slash minus the mass of the electron, and that is then the meta Lagrangian which is compatible with our geometry for the complex phases of psi. And then the action should depend on curvature, but in a Lorentz invariant way, of course. So it depends on f mu nu. But the simplest Lorentz invariant term that you can write down is this one with some normalization like 1/4. And then you have the QED Lagrangian identified as the simplest possibility of a theory which contains a Dirac spinor defined on this curved internal space of complex phases, and which also depends on the curvature of that internal space. So this is the second motivation for gauge invariance and for the QED Lagrangian. Completely different kind of motivation than the first one, but both motivations are obviously important, and both of them give you ideas how to generalize from here to other theories. And this is the reason why different ways of looking at things and different motivations are important, because you can draw different kinds of connections which are always important. Therefore, let us write some comments on this. So, as I just said, this is a new perspective on QED. And this is important because, as we already have seen, it can be generalized to non-abelian Yang-Mills theories. And it provides an obvious kind of motivation for them. So Yang-Mills theories are simply the same, where you have not one psi, but a column of different psis. For example, a column of psi up quark, psi down quark, or psi electron, psi neutrino. And then here Somewhere you have a 2 by 2 matrix, and that means the A's would become 2 by 2 matrices in that space of up quark, down quark, and so on. Then you get non-abelian theories. So the second connection or a generalization of this whole set of ideas is, of course, general relativity, which is based on curvature as well. So there is a very close analogy to general relativity, which works as follows, namely the connection field A mu, in other words the gauge field, that defines parallel transport in our internal space. And in general relativity we have curved geometry of space-time, not internal curved geometry, but curved geometry of space-time. And there the parallel transport is described by so-called Christoffel symbols, gamma, rho, sigma, mu. The mu index is analogous, and it corresponds to which direction you do the parallel transport into, and the rho sigma corresponds basically to a matrix in 4-dimensional Minkowski space. So these are the Christoffel symbols. If you have learned or thought about general relativity, then you might know that those Christoffel symbols have quite complicated behavior under coordinate transformations, which reflect the fact that they are similar to A mu connection fields, which are exactly not covariantly transforming under transformations. That is exactly the point. They are the objects which make up covariant derivatives, which are then, as a combination, covariant, but these objects themselves, they have complicated coordinate transformation rules, like A mu has an inhomogeneous gauge transformation law. Then there is the field strength tensor or curvature tensor, and that has the analog of the Riemann curvature tensor of the space-time geometry. Again, mu nu has the same meaning here, and rho sigma is a matrix basically in Minkowski space, 4-dimensional space. That is the Riemann tensor. And then you can ask the same question, namely, first of all, you can ask yourself as a theorist, should we allow or not curvature in our space-time? Should we allow for that, yes or no? It is your choice to write down a theory which doesn't or does allow curvature in space-time. And once you decide to allow it, then you can ask, should that curvature of space-time be a dynamical quantity which has its own equations of motion, or is it a fixed curved space-time in the background which is not influenced by us but which is just fixed? And the decision of general relativity is to say curvature of space-time is a dynamical quantity. There are equations of motion for curvature, and that means the action and the Lagrangian should of course depend on the curvature, and then you minimize the action with respect to curvature and get equations of motion for it. Therefore, how do you obtain the Lagrangian for general relativity? By simply asking what is the most general or even the simplest Lagrangian which depends on curvature and otherwise is covariantly defined, but which is also Lorentz invariant. And then you come up with a simple Lagrangian, namely the Lagrangian for general relativity is given by, first of all, a meta-Lagrangian, which contains all sorts of meta fields like psi, electron fields, and so on. And in this meta-Lagrangian, you must, of course, again replace, like here, normal derivatives by covariant derivatives. And covariant derivative does not mean this one here, but it's covariant with respect to general coordinate transformations in space-time. And in those covariant derivatives, the Christoffel symbols will appear. So, therefore, whenever you have a normal derivative, there will be a linear combination between derivative and some Christoffel symbol. that is an automatic consequence of making the meta part of the theory invariant under local general coordinate transformations. And now comes the thing with the curvature, and so you write down the simplest Lorentz invariant term, which depends on the curvature tensor, and that is in this case even simpler than this one, because you can construct directly a scalar out of this quantity by contracting the 4 indices in a certain way. There is a normalization which is sometimes called 1/2 kappa times r, and r is simply the following. You take this curvature tensor, and the first and third index, they are first of all contracted, rho rho, and then the other 2 indices, sigma nu, they are contracted with a metric tensor. And then you get an object which is completely invariant, and this thing can appear in the action. And that is the action of Lagrangian of general relativity. So, and as simple as that, you can obtain the Lagrangian for general relativity, and if you now minimize the action, then you obtain the equation of motion for curvature, which is the Einstein equation for gravity. Yep. Is the so-called curvature scalar or Riemann scalar. The Ricci tensor has 2 indices. I forgot which 2 indices you need to contract in order to get the Ricci tensor, but that is the Riemann curvature scalar. So in a way, this also looks like kind of a unity in fundamental physics, because as you know, we would say today that there are 4 fundamental forces in physics: gravity, and the 3 forces of the standard model of particle physics. And the 3 forces of the standard model are described in this way by such Yang-Mills theories, which can all be understood by that curved geometry of some internal space. Whereas gravity is described by curvature of space-time, and so in this way you see that actually all 4 forces that we know of are described by this curvature idea, and so maybe there is something deeper to this idea than it seems at first sight. So our first motivation, just to remind you of that one.
طبعا هنا أريد أن أقول كلاما هو أنه هذا يصدق ما توصلت إليه وذكرت سابقا، أن المساواة أو التكافؤ بين يانغ ميل إيكويشن أو بين الكيو اف تي أو كيو اي دي إيكويشن ومعادلة أينشتاين هي عبارة عن النقيض، بحيث أنه اللاجرانج بالنسبة للكوانتم فيلد يعبر عن طاقة مطرودة من التفاعل، بالتالي يحصل تخفيف للكيرفيتشر، ومعادلة أينشتاين عبارة عن طاقة موجودة في التفاعل وتعمل تزيد الكيرفيتشر. المساواة الجمع بينهما أو المساواة بينهما تعطينا طاقة موجودة في التفاعل، وكيف تتصرف هذه الطاقة المطرودة موجودة في التفاعل ولتطرد من التفاعل. إذن الإف مينيو هو الذي سنجد فيها حلا كبيرا إن شاء الله في بالنسبة لكتاب القادم الحلقة 54. سيخبرنا الإف مينيو عن لماذا لماذا هذه الديجريز اوف فريدم اوف يعني في بالنسبة للكيو سي دي أحمر وأخضر وأزرق وهكذا. لكن هنا يؤكد على كلامي أنه إذا حاولت أن تساوي بين الكيو اي دي والأجراء وأينشتاين تعطينا مساواة جميلة، ولكنها إشارة سالب. هذا يعتبر طاقة زايدة في التفاعل، وتلك تعتبر طاقة مطرودة من التفاعل. بالدليل على كده أنه في يعني مثلا في هذه المعادلة نجد أن معادلة ديراك يساوي 0، أليس كذلك؟ معادلة ديراك يساوي زيرو، والإف مي نيو إف مي نيو يساوي زيرو. طيب هذا يعني أن في معادلة أينشتاين نجد أن الحد الأول لا يساوي زيرو، إنما الحد الأول والحد الثاني يساوي زيرو. يعني الحد الأول ناقص الحد الثاني يساوي زيرو. وتلك في معادلة اللاجرانج في كيو دي إنه معادلة ديراك واحدة يساوي زيرو، والإف مي نيو مضروب في إف مي نيو يساوي زيرو. يعني بما أن سويت زيرو معناته أثبتت ما يسمى بالكونتينيوتي إيكويشن اللي هو معادلة الاستمرارية، وبالتالي ستتصرف كأنما تحسب الطاقة المطرودة بالتفاعل بدلالة الطاقة الموجودة في التفاعل. وهذا واضح أنك ستلغي عندما تستخدم الكونسترينز ستلغي المعدلات الزمنية أو الاشتقاقات الزمنية. إذا اشتغلت الاشتقاقات الزمنية فأنت تعبر عن طاقة مطرودة من التفاعل. فالكونسترينز هي التي حكمت علينا، طبعا هي لها مصلحة يعني فائدة كبيرة جدا، لأنها حكمت علينا أننا نحسب طاقة مطرودة من التفاعل، وهذا جميل جدا للكيو اي دي. لكن أعطتنا نصف الحقيقة. الحقيقة هي طاقة موجودة داخل التفاعل موجودة في التفاعل وطاقة مطرودة من التفاعل. الكونفليكت الذي يحصل بينهما تعبر عن الاكشوال رياليتي اللي هو الصراع بين الفضاء ثنائي الابعاد والكتله. يعني السبب الذي جعل اللاجرانج لكيو اي دي يعتبر طاقه مضروبه بالتفاعل اننا سنستخدم الكونسترين وهو ان نجعل المشتقات الزمنيه يساوي زيرو. هذا الكونسترين الاول. الكونسترين الثاني ان نجعل المشتقات المكانيه يساوي زيرو، لكن سياتينا اشكاليه هو ان المشتقات المكانيه ناقص المشتقات الزمنيه لا يساوي زيرو، وهذا ما يعطينا معادله ديراك. لكن هنا ما فعلنا هو كالاتي: ودمجنا بالكلاس 2 كونسترين مع كلاس 1، لان الاف مي نيو مضروب في اف مي نيو تعتبر الكلاس 1 كونسترين، فبالتالي جمعنا الكلاس 2 مع الكلاس 1. وهذا لا يضر، لانه الكلاس 1 اصلا يساوي زيرو، والكلاس 1 موجود اصلا داخل الكلاس 2. ارجع لحلقات الاولى والثانيه والثالثه. فالكلاس 1 اصلا موجوده في الكلاس 2، فهذا لا يضر. لكن هناك اختلاف في الكلاس 2 وهو ان جعلنا المكان يساوي زيرو، وبالتالي اي طرح بين الاشتقاقات المكانيه والاشتقاقات الزمانيه اذا لا يساوي زيرو فان ذلك تتحمله الكتله، تظهر داخل الكتله ولكن لا تظهر خارج الكتله. ولهذا معادله ديراك هي التي تتحمل هذه الفروقات بين الاشتقاقات المكانيه والزمنيه، والتي تتحملها ام الموجوده في هذه المعادله الواضحه الجليه امامنا. هذه المعادله انظر الام، ان هذه ام هي التي تاخذ هذه تتحمل هذه الفروقات. وهذا ما سيحصل ان شاء الله في كتاب الحلقه 54 انني ساحمل ام هذه الاختلافات في الاشتقاقات المكانيه والزمنيه، وهذا ما يعطينا الايسوس بين اللي هي الدبلت بين ما ذكرته سابقا الفيرست جنريشن والسكند جنريشن والسكند جنريشن، بحيث انه الاب والداون كتلتهم مختلفه من بعضها البعض، التارم والستريج كتلتهم مختلفه من بعضها البعض، الطب والبطم كتلتها مختلفه من بعضها البعض. كل هذه حتى عندنا الالكترون والنيوترينو ايضا تعتبر من الايسوس بين الالكترون والنيوترينو. شوف الكتله مختلفه كيف، اختلاف كبير جدا جدا. عندنا ثاني الميون والنيوترينو ايضا في تحلل باي ميزون يعطينا ميون ونيوترينو. هذا ما سترونه في كتاب القادم ان شاء الله، انه الباي تحلل الباي يعطينا ميون ونيوترينو بنسبه 99%. هذا الباي بلس باي ماينس، اما باي نيوترال يعطينا ايضا لا يعطينا ميون ولا يعطينا 2 فوتون. 2 فوتون يعطينا من النوع جاما، طاقة عالية طبعا من النوع جاما، وهي برضه 98%. بعد ذلك هناك نواتج أخرى، مثلا إلكترون بالنسبة للباي نيوترال، وبالنسبة للباي سالب موجب يعطينا إلكترون نيوترينو بالمناسبة، والثاني يعطينا يعني انظر إلى الفرق بين إلكترون نيوترينو بالنسبة في الباي موجب سالب، والفرق بين الميون نيوترينو فرق كبير جدا. الميون يساوي 200 مرة كتلة الإلكترون، يعني الميون كتلته 106 والإلكترون كتلته نصف ميجا وتلك 106 ميجا. شوف الفرق. وهذا عبارة عن فيرست جنريشن وسكند جنريشن، وهذا طبعا يعطينا على أنه إذا زدنا معدلات، إذا زدنا طاقة التفاعل فإننا سندخل أعمق في التفاعل، وبالتالي سيكون المشتقة، الفرق بين المشتقة الزمنية والمكانية داخل التفاعل عميقا أكبر من المشتقة المكانية والزمنية خارج التفاعل. وبالتالي الطرح بينهما يعطينا فرق كبير. هذا الطرح يتحمله، هذا الفرق يتحمله الكتلة مباشرة، وتظهر اختلاف كبير في الكتل بسبب هذا الفرق. جميل جميل جدا.
Came from a completely different point of view, namely it came from quantum mechanics and quantum field theory, where we studied the free particles of spin 1/2 and the free particle of spin 1, and we derived that in order to have a consistent quantum field theory of spin 1 free particles, we needed interactions which have this gauge invariant form where the A mu couples to a conserved current, and then we were led to the QED Lagrangian, and of course it's the same Lagrangian, therefore we can in hindsight interpret this in a geometric way. But in the second way of motivating things, we did not know anything about quantum mechanics. The discussion is purely classical. Here there is no quantum mechanics involved whatsoever, just the classical development of ideas, and then you obtain this unified picture of all the gauge forces and of gravity, which is quite nice. And so what is the more correct point of view is of course not known, but both points of views are important and give rise to further investigations and generalizations. Let me just write down 5 more minutes comments and then we can go to the exercise. Comments on the equations of motion. So the QED Lagrangian is at the top, so I will not copy it anymore. But what are the equations of motion following from that Lagrangian? There are 2 equations of motion, because we have said that not only the psi is dynamical and there is an equation of motion for it, but also curvature is dynamical, which means that there is an equation of motion for A mu. A mu is a dynamical variable. We have to minimize the action with respect to A mu and get an equation of motion in this way. What is the equation of motion following from Euler-Lagrange with respect to A? That is of course the Maxwell equation. It is the Maxwell equation because that is essentially the Maxwell-Lagrangian. Maxwell-Lagrangian, just that the interaction term for A is now hidden inside of this covariant derivative. But we get exactly the Maxwell equation. D mu F mu nu is equal to J nu, where that left-hand side of the equation comes from Euler-Lagrange applied to the F mu nu term, and the right-hand side comes from Euler-Lagrange applied to the other term. And in fact, this J nu is now specifically given by the derivative of the QED Lagrangian with respect to A nu with a minus and lower index here. So that is the outcome of Euler-Lagrange. And the current is given by plus E times Q psi bar gamma nu psi. So we have here an explicit representation of the electromagnetic current. The Maxwell equation looks like the usual one. There is a current on the right-hand side, which is the source of electromagnetic fields. But here the current is explicitly given in terms of the electron field. So we can say that we have Maxwell equations which give the dynamics of A mu in terms of psi. So normally in classical electrodynamics, you solve the Maxwell equations and study their implications, and all the time the current that you use, which is a source for the fields, is given to you from somewhere, from externally. You either set it to 0 or you set it to something, but whatever you do, the current does not follow from solving equations of motion, but the current comes from external information, and once you know it, you can calculate what the fields should be. And here the current is given in terms of the electron field. So once you know the electron field, you can calculate the electromagnetic field, which follow as a consequence. Good. Now, what are the equations of motion for psi? The equation of motion of psi is the Dirac equation, namely I d slash minus m acting on psi equals 0. That is the Dirac equation with interaction, where we have here a covariant derivative that depends on the electromagnetic field A mu. So this is the Dirac equation, and it provides the dynamics of in terms of A mu. Okay. So here you have given the field, and once you know the field, you can solve the equation, and you know that the time dependence of psi. And by the way, in macroscopic terms, that would be the Lorentz force acting on a particle, like the electron particle moves in an electromagnetic field. It feels the Coulomb force and Lorentz force and so on, and that is exactly the meaning of this equation here, just in more microscopic terms. So, the difference now that I want to highlight between this and maybe earlier theories that you have seen in theoretical physics is that the theory here is kind of intrinsically complete. There are no loose ends. In your discussion of Maxwell equations in electrodynamics lectures, you assume the current as an external information, and then you solve for the fields and you get something. In other contexts, you know the field and you want to know the time dependence or the trajectory of particles moving in terms of the field. But here the theory is complete because there is an intrinsic, let's say, dependence of both fields onto each other, and so therefore you can get a complete solution which simultaneously fixes what the current is and what the electromagnetic fields are. And so the theory has this intrinsic completeness to it which singles it out compared to many other theoretical frameworks. And that is the remark I want to make. So it has the character of an intrinsically complete theory. And of course, this kind of theories is what we are desiring in fundamental physics. In particular in particle physics. Okay, with this remark, I have sufficiently motivated and defined QED, and we can stop and we can turn to the exercise, and in the next lecture we will do examples of QED processes and discuss the physics of the impact of that theory. Okay, so let us come to the exercise.
طيب خلاص كده عرفنا الحاصل وعرفنا كتابي القادم هذا 54 كيف سيستمر إن شاء الله. نسمع أخبار جميلة جدا عن انتهاء من كتابي وحل أهم شيء، وحل QCD إلى الأبد، مشكلة QCD إلى الأبد، بدل أن تكون ديجريز فريدم قائمة بذاتها، لا نربطها بالفضاء الرباعي الأبعاد هذا طول عرض ارتفاع زمن، وبالتالي نكون حللنا مشكلة الجاذبية والكوانتم ميكانيكس، وأدخلنا حقق حمل الجاذبية في الكوانتم ميكانيكا بإذن الله تعالى. وهذا البروفيسور قدم لي هدية من ذهب، يعني قدم لي شيء جميل جدا جدا، أنني أين أبحث في هذا الموضوع. تمام. السلام عليكم ورحمة الله.